Measurement calculations and quality control in density sampling. And I've changed it to a very brief introduction on the subject because I had to do some really serious editing. I realized that there's a lot more to this subject than one thinks at first. So we're going to say, let's talk about density. What actually is it? Because interestingly, you ask people and you get some very strange answers. So why do we need to estimate it? And remember, and I'll explain why I use the term estimate. We don't actually measure it. And what happens if this density estimate isn't accurate? So what is density? So density is the amount of stuff in a defined boundary. Now, I use this word very specifically. Many years ago, I was a physics student, and we had a long discussion in one of our classes on what actually is in the universe. Okay, so this is a major problem with atomic physics. What are we measuring? Okay, so, and the professor eventually came up with this definition. It's the amount of stuff within a defined boundary. Now, when we're talking about density, we're normally talking about physical, so-called physical stuff, which is matter or energy. Right? There are other things that you can talk about besides things that you can physically touch or measure. So we're talking about physical stuff, which is matter or energy. And in most cases, in geology, we're talking about something physicists call matter. Right? And it's anything that has mass and takes up space. Right? And there's a reason why I'm going to give you this, because one of the measurement methods that we use really depends on this definition rather than what you were maybe taught in high school. So matter is made up of protons, neutrons, electrons, and sometimes leptons, quarks, and their antimatter. And there's some other stuff that's called dark matter, right? So the only thing we're going to be concerned about currently is matter that's made up of protons, neutrons, and electrons that fill a positive dimensions in 3D space. All right. Okay, that's actually our definition of what we're trying to measure. There are lots of other things that can happen. You can actually measure things like energy density. All right, but the methods I'm going to look at now are, strictly speaking, one of the methods could actually be considered measuring energy density. So it's not as straightforward as most people think, but we're looking at matter and energy in the normal sense of the word. All right, so why is it important? Okay, the simple answer, obviously, we want to know how much mass we have in some volume. The reason we want to know this, obviously, is we want to know how much stuff there is for whatever reason. And in mining, yeah, there are a lot of reasons. We'll go through that just now. So knowing the density, especially in a sample, so we're talking about sampling here. Knowing the density, we can scale up the mass proportions of a small sample to the mass of the larger deposit, because obviously we can't put a 10 million ton deposit on a scale and measure its mass. Right? We have to have some other way of doing it. So in a simplistic example, and this is very simplistic, if the average amount of gold in a 50-gram sample is 0.0005 grams, all right, that translates to a 10 grams per ton. Okay, it's not actually density, it should be a content. So that in a 10 million ton deposit, you would expect basically 10 tons of gold. All right, so that's the reason we measure density, so that we can scale up to the large deposit and estimate the amount of stuff in that volume of rock. Okay. All right. Why is it important? Yeah, we need to move, in mining, we need to move rock. Okay. And we need to know how much rock there is so that we can estimate things like the content of the economic material. Okay, so we can estimate the revenue. We need to know what size plant we need. Okay, what size plant do we need? So we need to know the volume and of the material, but we also need to know the contained mass. And there's a whole lot of calculations in the mineral processing that depend on mass and density. We need to know how long it will take to extract the production rates, to extract given certain production rates. Something, if anybody who works really well open pit and certain types of underground, how many trucks do we need to move the rock? A lot of trucks are filled by volume, and a lot of trucks have weight limits. Right? So if you don't get the density or the mass that's going to go in that truck right, you're going to have either too many trucks or too few trucks or the wrong size trucks. Right? Things like fuel. Right? How much fuel the trucks are going to require to move the rock. Right? It takes a lot more fuel to move 10 cubic meters of iron ore than it does to move 10 cubic meters of coal. Right? Just think of the density. So the 10 cubic meters of iron ore has broken iron ore probably has 3 or 4 times the mass of the same volume of coal. Right? So that's an expensive mistake if you don't get the density right. So getting this density wrong has some really profound implications for the revenue and on the operations. And I think most geologists don't appreciate the extent that things can go wrong if you don't get that density correct. All right. So we're going to measure density. And measuring density is not as simple as you were taught in school. And by school, I even mean university. So density, there's a lot of considerations. There are various methodologies. There are all sorts of problems measuring densities. Okay. So measuring this. And if somebody, I think we're probably going to have a reasonable amount of time here. So if somebody really needs a question, just put up your hand. So measuring density or mass. So in order to measure density or estimate density, we don't measure density, we estimate density. At a minimum, we need 2 measurements. We need a measurement for mass, and we need a measurement for volume. Right? And again, mass is generally not a direct measurement. Okay. Instead, we measure some property of a material that is correlated with mass. Right? So we measure the downward force on an object. We generally refer to this as the weight. There's something else we measure. It's an electron density, hence my definition of matter. So it's protons, neutrons, and electrons. So your gamma logging, which is a nuclear tool, measures electron density. And then there's another radiometric tool. It uses something called the photoelectric effect. If you want to know what that is, there's a whole there's good explanations on Wikipedia. So again, this has to deal with some sort of electron density. Right? So we're not measuring mass in and of itself. We're measuring some feature of an object that is correlated. All right, and I use the term correlated with mass. Right. So we measure these things. We measure the downward force of an object, electron density, photoelectric. They're proportional to the density of a mass. All right. I'm assuming that we're going to be giving you guys these the slides. So in all of this, I've left various links that can give you better explanations of what these tools do. Okay, obviously downward force is just a normal scale. Most of us know that. The logging techniques for electron density and photoelectric are explained in these links below. Right? So you can go and read through them. They're fairly straightforward. They don't require a degree in physics to actually understand them. Okay, measuring volume. Measuring volume tends to be a little bit more complicated. So we generally measure volume, in two different ways. Okay, it can be calculated or it can be estimated from several measurements. We have direct measurement of dimensions. That's taking a ruler or a caliper or something and physically just measuring the dimensions. You may have something with a known volume. Again, somebody measured it somehow. I'll show you some examples of known volumes a bit later. So things with a known volume is a graduated cylinder that you use in, the normal one that you use in your science classes or for whatever. There's what we call the coffee can method. That works pretty well. You generally know that. You can measure that using liquid or something. You have boxes. You have bags. Bags usually aren't good for dimension measurement, but boxes and cans, any kind of a rigid container works well. And you can measure the dimensions of regular objects, but you can't measure the dimensions of irregular objects very easily. Where we have irregular objects, sized objects, we generally use what they call displacement method. So it's putting a solid normally in some sort of a liquid, and we measure displacement either by overflow or by looking at the change in height of a column of liquid. Again, I'm going to show you pictures of this. Those are the two easiest ones. Now, and I should say fluid and fact, because we use either liquids or gases for a displacement method. Right. So the nuclear methods, strictly speaking, don't use a volume, but they do use a fixed distance between a source and a target. Okay, so that eventually translates into some sort of a mass volume, a volume for a mass. Okay, so yeah, and I'm going to show you how these nuclear methods work with a couple of diagrams. Right, so the simple measure. This is your coffee can, or in case I'll show you the next one is beans. Right. Normally we measure the diameter, just because trying to measure the radius on one of these is really, really difficult. Okay. So we measure the radius, we measure the height. We get the usual volume equals pi r squared times the length or the height. Then we put it on a scale and we measure the force of gravity. So scales measure weight. Okay. In your digital scales, you will have a calculation that translates that force into a mass, right? But strictly speaking, we can't measure mass, we can measure weight. What else? Okay, that's how a digital scale. In the old days, people had a balance, and so you balanced it against a known mass of material, right? Then you would have what they call a mass balance. Right? We still get those sometimes. You'll still get mass balance scales, but they're less and less common. Okay, so the method is you measure the dimensions, you calculate a volume, you weigh the object, and that's the correct term. You convert the weight measurement to a mass. So like I said, your digital scale does this for you. And you calculate mass divided by volume, and that will give you a density. Right, so this pretty much works for anything, assuming you can actually measure the volume. Okay, so this is my can of beans. Regular measure, so I'm measuring, in this case, if you have a container, a word of warning, you must measure the inner dimensions and not the outer dimensions. Okay, because again, we want the volume. So this ruler is measuring the inner dimensions of the tin, measuring the length of the tin. Again, it's an inner dimension. Just using a decent quality ruler. We're going to discuss decent quality later. So I get a volume of 467 milliliters. Okay, then I put it on my scale. I come up with 488 grams. All right, so it measures the mass, it does the conversion, it measures the weight, it does the conversion to grams, 488, and I've calculated a density of my, yeah, it's a bad one, because the one thing I haven't done here is I haven't taken into account the weight of the steel. Okay, and if I do that, so my tin says I'm supposed to have a mass of 400 grams in here. I'll tell you right now, I probably don't have 400 grams in here. Okay. But that's the calculation. On the left, one of the things that I want you to look at is this density equation. So I say density equals mass divided by volume equals an F, which is a force, right? Or your weight, divided by pi r squared L, and then there's this G, right? So gravity, all right, G is the gravity, all right, strictly speaking, it's not constant, okay? And I've given also a link about this acceleration of gravity versus latitude and elevation. Now, for most cases, we treat gravity as a constant. And for a lot of our measurements, we don't need to worry too much about how density changes both with elevation and with latitude, right? Because obviously the Earth isn't a circle, mass is not distributed equally over the Earth, and gravity is any force, it's a inverse distance squared measure. Right, so the farther you get away from the Earth's center of gravity, the less the acceleration due to gravity. Right, so gravity is not as strong. This only becomes a problem when you're measuring density if you are either at very high altitudes. Okay, so you're up in the Andes or the Himalaya. If you're in the Himalaya, you have two other problems. You have the mass of the Himalaya, which is well known to affect the measurement of gravity. Okay, so things like large mountain chains affect your gravity, your elevation, and your latitude. Okay, so it's something to be aware of. You may not have any kind of problems if you're measuring large masses, but if you're measuring small masses, there's possibilities for some problems. The other one that to be really careful with is that G, because it's an acceleration. If you have magnetic rocks and you're trying to measure mass or anything with magnetic rocks, make sure you're not near any kind of strong magnetic field, right? Because what happens is the magnetic rocks get pulled towards the magnetic field, and that's also a force, and your scale will measure that force. Right. So like those of you who work in places like the Bushveld or on certain types of iron ore deposits, just be aware you don't want to be near an electrical substation or something when you're doing your measurements. All right, they're small, it may be a small change, but again, that magnetic force depends on the mass of the magnetic material, right? So the bigger the magnetic material, the bigger the error. Yeah. Right. So gravity, remember the gravity issue. So for now, you can treat it as a constant, but just be aware in certain situations, you can get errors. Okay. Displacement. Now this is where things get a little bit more complicated. Okay, so this is what I'm showing you here is your basic pycnometer method, right? You can weigh the object with something. Okay, this is just a hanging scale. You can use a normal scale, whatever. So you weigh the object and you obtain a mass. You fill a container with liquid. This is what you call a graduated cylinder. And then you immerse the solid in the cylinder and record the change in the volume. So the difference in the volume between the cylinder without the rock in it and the cylinder with the rock in it is your volume. You do your normal calculation. Okay. This is how all pycnometers work, regardless of the fluid that's used. So whether you're using water or some oils or some gases, it all works the same way. All right, so again, it's relatively simple. This method tends to work for small masses. It's not good for huge masses. So there are various ways of doing it, but this works for small masses. They tend to use some version, a more sophisticated version of this in most laboratories, especially commercial laboratories. Okay, so it works nice on a desktop or a bench. Okay, this is another version of the displacement method. This is better for slightly larger masses. It works for your core, it works for your bigger rocks. You can set it up very easily and cheaply with equipment from, as long as you have a decent scale, the rest you can set up from, like a hardware store or something. You have a bucket filled with fluid. You have a weight suspended from a scale. I mean, it's always a suspension. The fluid is filled up to an overflow level. Then you drop the mass into the water. The volume that overflows will be the same volume as the fluid. And then you're going to measure a different weight. And this is what they call the buoyant weight. Okay, so what happens is that the mass doesn't always sink exactly to the bottom. Right? Sometimes it does, but if your balance is set up correctly, the mass should not sink directly to the bottom. And there is an upward force called the buoyant force that's pushing on it. And that force up is the difference between your two weight measures. All right. So this particular setup is the basis for most density scales. Not all density scales measure the overflow of the fluid. Sometimes they just measure the weight out of the fluid and the weight in the fluid, and then there's a calculation that you can do to estimate a mass. Okay. It's not very good. It's not good at estimating a volume if you don't have the overflow method. Right? But like I said, most of your density scales work on this method. Okay. The other one I want to look at on this as well is, again, it doesn't matter what the fluid is in principle. So it's normally liquids. It doesn't have to be water. It can be something else. Right? And I've got a slide later to just discuss a couple of the other issues that you might want to consider. All right, so we also use this one where we use sealed samples. Porous samples with wax. Oh, plastic wrap. Okay, so yeah, plastic wrap, I'll discuss the issues with around plastic wrap. It should be sealed with a heat gun, not just wrapped up in just random plastic, okay, because it causes problems. Okay. Again, you can use this method with the porous wax. The plastic wrap works for regular shaped samples. It doesn't work for randomly shaped or irregular samples. Porous wax can be really good if it's used properly. And we generally use those with these immersion methods. Okay, this is when we have porous rocks and we want to make sure that the air inside the pores is retained. Okay, there are cases where you might not want the air in the samples retained, where you want to actually fill the sample with fluid. The density measures for nuclear methods. This is a gadget. Okay, it sends out gamma radiation, measures attenuation of the radiation through the mass. In this case, the first one measures attenuation. So the little red dot at the bottom is the source. It sends out a gamma ray. The box has a sensor and it measures the difference in the radiation between the source and the sensor. The second one is a little bit more complicated. What it's really measuring here is the electron density. Remember I said the photoelectric effect? It measures how the gamma rays deflect off of the electrons effectively. That's a slightly simplistic explanation. And again, there are links that explain how these work. Okay, this particular method is used, and I even have pictures. This particular method is used in construction literally on a daily basis. All right, this is how they check to make sure that the roads have been compacted correctly. And we use this on tailings dams. All right, this is generally in use. This is one of DRD's tailings dams where they're measuring the density. So you scrape off the loose surface. You have to go down to the compacted surface. You have a plate to secure it in place. This guy's putting a plate and a rod in. The instrument is set up over the plate and the rod. It's left to take its measurements. And again, there's software that will turn the measurements that the instrument takes into an estimated density. Right. Okay, so it works really, really well. Okay. It is a surface measure, so you need to be careful. The other one is you need training. So not just anybody can use this. You really need to go for training and learn how to use these properly. All right. Your downhole density measure. Right? It works the same as the surface machine. It has a source and it has a receiver, and it measures either the electron density or it measures the attenuation through the mass. Right? Same calculations. It's just a slightly different configuration because of the nature of the environment that it's being used in. Okay. All right. All right. What happens when you don't have a small sample? All right. So this is a picture, and sorry about the quality. This actually comes from a publication. I've given you the link. This was actually a GeoBulletin article a few years ago on industrial minerals, measuring it. So this case is bentonite, but it works for any loose material, and it's really good for measuring broken rock. You get a box where you know the volume. So in this case, it's a 1 meter cube box. You get a front end loader and you fill the box. Okay. In this case, he's leveling off the top, and then you will take that box to some sort of measuring station. Now, it could be a weighbridge. Most weighbridges to measure which is about 1 ton here, may not be sensitive enough, but you can get something called a crane scale. All right, again, this is used all the time in a lot of industries. I've given a link. This is a South African company that sells all kinds of scales for all sorts of purposes. So you basically hold this, you can put it on the fork of a front end loader or a shovel, and you can suspend the box with ropes with the crane, and it will actually measure the mass or the weight. It'll measure the weight of the stuff in the box. And again, you can do your calculations, right, to calculate a density. That's big volumes. All right, small volumes of loose material. So this is the coffee can method. All right, it works really well. The only potential problem here is making sure the compaction is correct. Right, same way. All right, your RC drilling. So again, this constant volume, you need to just weigh, but if you're going to do it, you need to weigh the entire sample. If you're splitting off samples, you need to weigh both the small sample and the big sample and correct for the plastic or whatever bags you're collecting it in, right? And then you use the known diameter of the drill rods. And again, you can calculate a density of the sample. All right, quickie calculations. Your basic calculation, mass volume or force divided by volume times your acceleration, right, to be correct. Your volumes are generally length times width times height, or pi times radius squared times height for cylinders, or as measured by displacement. Okay. It gets a bit more complicated for these scales, and I've given you the actual calculation. There's also, this is the Mettler scale website, okay, where they actually explain how to calculate a density from the measurements from their scales, right? So you need the density, to get the density of the sample, that's this P or rho strictly. You need the weight, obviously, of the sample in air, the weight of the sample in, they call auxiliary liquid. Explain why. The density of the liquid, auxiliary liquid, and density of air. Okay. Temperature of the liquid must be taken into account. So for those of you who work, you know, in a climate controlled laboratory, or this isn't so much of a problem, but there can be a difference in some measurements if you're, say, in the middle of the Kalahari and it's 40 degrees outside. Okay, so just be aware that temperature does affect the measurements at some point. And the reason for the calculation like this is, again, you don't necessarily need to use water. You can use other liquids. Right? There are cases where you might want to use an oil instead of a water, right? It also, yeah. And in the laboratories, they will use different liquids depending on what they're trying to measure. All right. So for real bulk density, which is mostly what we want, that PO, this auxiliary liquid is water. Okay. And it should be clean water, not hard water, not brackish water. You want as few dissolved solids in the water as possible, because the dissolved solids affect the density. Okay. And we're not measuring, we don't want a specific gravity. Specific gravity is something else entirely. So be careful with your terminology. And I'll show you later, know the difference between a bulk density and a specific gravity, because they really aren't the same thing. You need to make corrections for any sealed material, okay? So for the wax coating, you have a correction for the mass, the density. There should be normally for the buoyancy of the wax. And I couldn't find an example with the correction for the buoyancy. I used to have an old one. It's not done anymore, and that's a big problem, and I'll show you later where that brings in errors, but you really need to do the correction for the buoyancy of the wax. And there's a link as well. This is Michigan Tech University. It's from a civil engineering master's degree, but they give a really nice example of how to calculate bulk densities. And they show you how to do it, do the calculation with the wax and how to do it correctly. All right, plastic wrap. You may require a correction for the mass of the plastic. I don't recommend this method. It's just got way too many problems, but if you absolutely insist on doing it, just be aware that you probably have to make a correction for that plastic. All right, the other issues that we end up with. So this is some variations on constant volume. If you have thick sequences of friable core, you can't wax them. You can't obviously put them in water because it falls apart. And I've used this successfully. It's a core box method. You measure the weight of the empty core box. You're going to measure the weight of the core box with the core, measure the length of the core. And you should know, if you've done your logging correctly, you should know the diameter of the core and the recovery. And from that, you can calculate an approximate density. Now, this works really well for thick sequences of largely the same stuff. All right, so thick sequences of clay, sandstone, porphyry, copper, that sort of thing. And like I said, I've used this in really successfully for quite a few bulk materials. Trucks. All right, if you need to look at like broken ore, and I've had this question come up. So again, the bucket of a truck is just a container. It's not a good measure, and you need to do quite a few trucks because you need to get some sort of statistical average. But it's basically the same thing. You weigh the truck at the weighbridge. You want to weigh the truck full of ore. You have a roughly known volume. So you can calculate a volume and a mass. And the one issue correction that you really do need to look at is correction for fuel loss if you have to transport it over large distances. And the trucks are quite big because, you know, as everybody knows, like if you when you're driving to work and it's you in the car, you use a certain amount of fuel. If you have your family, your dog, and 2 weeks worth of luggage, you use a lot more fuel. So the mass of the vehicle is what did they say? The mass of the vehicle, the fuel usage, sorry, depends on the mass that the vehicle is carrying. So just be aware that if you're doing the trucks, correct for the fuel usage. And we got some known problems. All right, density. It's only for the sample which is measured. Materials are heterogeneous at the scale of the sample. You need multiple samples of the same material. Statistical analyses are necessary to arrive at a density for a larger volume. All right, you have to do the stats. So either classical estimate of a mean and variance or geostatistical to estimate spatial variation. And be careful, measurement errors are common and they can be large due to things like irregular shapes, porosity, incompetent or friar materials. Broken rock, really difficult to estimate a density for broken rock. That's so-called RC drilling, trenching channel samples, run-of-mine ore, and so on. All right, QC, this is going to be quick. Accuracy and of the measuring devices, accuracy and precision. We have the accuracy of the measuring devices. Buy decent quality rulers and tape measures, okay? Really, it's important. You need to check your tape measures for stretch regularly if you're using cloth tape measures, or even some of the metal ones. Some of the cheap metal ones tend to deform. If you're using metal ones in very hot climates, also just check it against something, right? Metal tends to expand with heat. Calibrate your scales every day or every use session. You need to plan a quality control sample sequence, and you're going to try to use more than one method on some of the samples, or at least on duplicates. Okay, so quality control samples, you purchase a decent set of masses, standard masses, all right? Your scale should come with one, but if not, you can get some, and this is really important. If you don't calibrate your scale, you have no idea what you're measuring. You have a set of standard rock samples with known masses and densities for calibration and for reference samples. You're going to pick samples for duplicate measures at regular intervals. And literally treat these as you would an assay, because it's the same. Okay, there's no difference between density measurements and your gold assay. So quality control system with duplicates, samples for second methods, and standards for calibration. All right, and for control samples. All right, so I want to just show you this again. Is from that GeoBulletin article, where some samples were checked using multiple methods. All right, so we've got some oxidized peroxenite. There's a vacuum pack method. That's really kind of cool. And the paraffin wax, and you can see that there are differences versus a caliper method. So they physically measured a decent cut piece of core, and then they sealed it in a vacuum pack. They sealed it in paraffin wax. All right. And you definitely have differences, okay? Look at what happens, if you look at the next one, SG6, competent peroxenite, look at what happens when you use cling wrap. All right, this is why you should not, please just don't use cling wrap. All right, you're trapping air. There's no way that you cannot trap air in there. All right, even using a heat gun and shrink wrapping it or whatever, right? And 3% starts to become a big problem. The other one is at the bottom here, paraffin wax on half core and spray lacquer on quarter core. Now there is a difference in them. The smaller sample shows a larger density than probably there is. We don't know anyway. I don't know for sure here anyway. But there is a difference between half core and quarter core. There's a difference between the wax and the lacquer. The one issue with small samples, all right, is that there are some errors that are absolute. They're not relative. And if you have small samples, you're going to end up with higher relative errors. So use the biggest piece you can get. All right, so I've got on here, some errors are absolute, not relative. Smaller sample will have a higher relative error always. So you must use the biggest sample you can possibly get. Wax is thick. You need to practice the wax. If you get this wrong, again, your calculations will be out, because very thick wax needs a correction for the buoyancy of the wax. Again, sources of error. Different people measure differently, changes in temperature, wear and tear on the scales, which is why you calibrate all the time. And your documentation. Documentation. One of the things I see often when I try to go and I do either audits or reviews is there's no documentation. So we need calibration records. Did you actually check to make sure the scale was working properly? In most cases, the answer is no, which means I don't know if that scale is accurate or not. Do you have measurement records? Quality control samples, almost never do I see those. Batch and date of records. This is another one you don't see very often. Who captured the information? As I said, everybody does it differently. Control charts by rock types. Again, never see this. Nobody bothers to check if it's consistent from batch to batch, or almost nobody. Statistical analyses for variability, outliers, and instrument drifts. Again, I almost never see this, and it's really important. Again, do you have the supervisor checks and sign-offs? Sometimes we see this. You also need equipment lists with service records, scales, and these things, they need to be serviced, all right? It's not just plug and play until they break. And lists of consumables, what you're using. And I'm running out of time here. And just a couple final notes. Learn the difference between dry and wet bulk density, between bulk density and something called skeletal rock density. So Google it. Specific gravity and density, they aren't the same thing. And learn some different methods, right? Quality control is important, and documentation is important. Don't be lazy. Documentation, we hate it. We all hate it. We know this. Do it. And in here, I've given a lot of links. These are various sources of information. So wireline methods, multiple methods, soils, for those of you who deal with soils. And this is the last one is a really nice, some videos by a manufacturer, equipment manufacturer. All right. And again, look at other disciplines, right? Yes. Are there any questions? Hello?
Excuse me.
Yeah,
excuse me. Yeah. For example, if you have a core of 1 meter and it's broken in different pieces, how much percentage do we have to sample to have a real, well, not real, but approx density? Yeah.
The whole core.
The whole core. Oh, okay.
Yeah.
Interesting.
Yeah.
Okay.
Look, you know what? One of the issues, and I was going to use this as an example. These are heterogeneous materials. If you want to know the density of that 1 meter of core, and you have a bucket big enough, you do the whole core. You can actually do it in pieces as well. You add up the masses. Okay. And you can do it that way.
Okay,
right.
Thank you so much.
So the bigger the sample, the better, always. Yeah, always. So tiny, and my rule of thumb is if it's less than 20 centimeters, just, you're not going to get a decent measurement. There's all kinds of problems with these mass balances. And like I said, there are absolute errors in all equipment. All right. The equipment has an absolute bottom limit that it can measure. All right. So the smaller the sample, the higher the relative error. I did see one. It's actually quite a cool gadget from Australia. I think it's in one of the links where they have a tray and you can actually put all of the pieces of that 1 meter on the mass balance and do the immersion method. It's a nice gadget and it's very expensive, I'm sure. But you can do a setup where you can actually, get a big basket and a decent scale and measure the whole thing.
Okay, thank you
Okay.
so much. Yes,
Yeah.
yes.
Again.
Kathleen,
Yeah.
yeah, so that slide you showed with the same material measured in the various methods.
Yeah.
I think it's 30.
Yep.
So that's quite an eye-opener, because it just shows you that, how do you actually choose the appropriate method for your material? I mean, you could use all of these and they all give different measurements.
Yeah.
I mean, we even see between the Archimedes and the pycnometer, we do see variances.
Yeah.
Is there any sort of hard and fast rule as to, what is the more appropriate method for your particular, say, commodity or material?
Yeah. So like I said, it's always a problem. All right. The best one obviously is something like a caliper method, if you can do it. But that you need regular, the caliper method, or what I call as a constant volume, those are obviously the best ones, because you don't have problems with fluid invading your sample and everything. Okay, it's often very difficult to do that. Okay, but if you can do it, that's great. If you have non-porous material, your standard Archimedes is also fine, but it really must be zero porosity, and you must have you can't have things like swelling clays in it. Right? If you have swelling clays and you stick it in water, it just messes up everything. All right, that starts swelling, it starts absorbing water into the crystal structure, and you end up with problems. And it also depends on, again, like I said, the friable rock problem. The friable rock problem, you can't handle the core. It literally will fall apart if you take it out of that box. So that's where I use the core box method, and honestly, it works great. There's a way of doing it, but we've done it I do it for some of the industrial minerals where I'm literally drilling gravels, and I can't use these other methods. The vacuum pack, I've never tried it, honestly. That could work really well, but again, if you have to use some big samples, because that plastic is really thick and it's going to affect your density measurement. Waxing takes an enormous amount of skill. All right, I think people underestimate the amount of skill it takes to do that paraffin wax and get a good coating. Because if it's very thick, you have to start doing a lot of corrections. So I had a client that used to use it, but they had 2 people that their only job was measuring density. That's what they did literally for years. And they were absolute masters at that waxing, but they would do, 200 samples a day. So they got really, really good at it. So again, you need to think it through, learn the methods, think it through. Pycnometers, I think, this is Nicole, you know what I think about the pycnometer method. All right.
Yeah.
All right, the other one, do not have the laboratory measure density, please. Okay, the guys in the lab do not understand what you want. All right, what they are measuring is something they call skeletal density. They often don't take into account the porosity, and most of the time the samples are way too small. I've had some really disastrous density measurements done at very reputable labs because they use 25 gram samples in their little desktop gadget. And they told me that my massive sulfide had the same density as my quartz matrix. Now, seriously? So
Yeah.
please, you need to use big samples, at least 500 grams. All right, or
Yeah,
more. And
I think
just
the
don't
challenge is-
send it out to the labs. They really don't understand what you're trying to do. Their density measurements are for something entirely different.
Yeah, I think the challenge is if your whole database is based on a picnometer, then you're
Yeah.
better off obviously sticking to that versus, changing now halfway through or
Yeah.
in
But
In
you need
present-
to make sure you make the corrections. You need to make the corrections for the bias in the measurements. So this is one of the things that people don't. Sometimes you can't get a good measurement. All right. But just understand what the bias is and make that bias correction.
Great,
And
thank you.
excuse
Yeah.
me, like a brief summary. What is important, this difference between dry and wet bulk density?
Okay. So if you're using your densities to calculate mineral resources from your assays, assays are always referred to dry bulk density from the laboratory. Okay, so in order to do your mineral resources and use your assay, you've got to use the same reference point. Okay, so in mineral resources, we generally don't use wet bulk density. We use dry bulk density. So your assays are dry bulk density because when it goes to the lab, they dry it out and they do everything without moisture. So we're going to calculate again without moisture. So when you're doing your samples, you want dry samples. Okay. And this is why if it has any porosity or swelling clays, you need to seal them if you're going to use the immersion method. Right? Because you don't want that water to get in there. You want to reference it as dry. Also, it makes sense in mineral resources, is you're going to de-water, whether it's underground or open pit, you're going to de-water and it's going to be reasonably dry, right, by the time you mine it. Now that's a bit of an overstatement because most of the rock actually, it's not really, really dry. But in most cases, we calculate it on dry. For some things like bauxite, you might want wet bulk density because it's soil and you may not be drying it out. Wet bulk density is used a lot in the geotech space, right? Because you're looking at soils. Even in construction in the roads, you might be also looking at wet bulk density. So wet bulk has water in it. Dry bulk does not have water in it.
In that case, we should use, for example, like paraffin wax. If we are going to, for example, if I have a rock with, for example, phyllic alteration or hydrothermal alter, it's important to use paraffin and make the corrections.
Yeah, you can use paraffin and make the correction, or if it's solid enough, you can cut it to a nice regular shape and measure it. But yeah, if you've got phyllic alteration, you definitely don't want those clays touching the water.
Okay, thank you so much.
Okay.
So we're looking at representative sampling and the issue of the theory of sampling. So the theory of sampling is essentially a framework of sampling theory and practice. So it covers a huge spectrum of sampling situations. And this is what I understood the course was about. So let's just see. The first thing I wanted to do was just to bring to your attention that there are historical reasons for sampling, and that the idea of sampling and theory of sampling is not something that just emerged over the last couple of years, but really this gentleman, Agricola, Gregorius Agricola, wrote this book, De Re Metallica, it was published in 1561, after he died, in fact. But you can see a picture of a gent here using a screen, and he's separating materials. So that's one of the sort of primary issues and things that we would cover generally when doing sampling. And the reason I put this in is because of the statement by Isaac Newton. He says, if I have seen further, it is because it is by standing on the shoulders of giants. So I don't want anybody to think that this idea of sampling and the theory of sampling just emerged overnight in recent years. It is embedded in work that was started way back when, and in particular the era during the mining in California, the Midwest and Colorado in the early 1800s actually to the 1900s. This was the work that was being done at that stage by David Brunton. You would recognize that name because he's the inventor of the Brunton compass. If you've ever done field mapping, you will have used one of those. This is Robert Richards. He was also did a lot of work in sampling. Henry Vezin is a remarkable character because in 1861, he designed the Vezin cutter. And here's a picture of the Vezin cutter. And what is remarkable is that he understood the principles of sampling. You can see by this radial cutter pattern of the cutter blades that he understood a lot more about sampling than he was probably actually given credit for. And we still use the same design these days. On the right-hand side here, there's a gentleman called Philip Ogle. He introduced the idea of gold cyanidation and the 8-hour mining shift and essentially changed the course of the gold mining industry forever. He published in the South African Institute Mining Metallurgy in this period, and he actually won this medal from Gold Fields. But just to let you know the amount of work that was done in these early days, there was a proliferation of literature. And in 1921, these two gentlemen, Sharwoods and von Bernowitz, just compiled a bibliography of literature on samplings, and they found 906 articles, papers, and books on the subject. So what I'm trying to say is that historically, sampling has been a very, very important issue. It's not something that's just emerged over recent years. Here you see the books written by Francis Pittard, really outstanding man in terms of his understanding of sampling and the theory of sampling and sampling practice. And then there are other books written also by Jeff Lyman, who's just finished a book, The Theory and Practice of Particulate Sampling, an engineering approach. And then, of course, Kim S. Benson has written this book, Introduction to Theory and Practice of Sampling. So these gentlemen have all contributed in one way and another to the wonderful work on sampling. And as much as we admire the work done by Pierre Guy, here's a picture of Pierre Guy and Dominique Francois Bongasson standing together. It's not just the work of Pierre Guy that was important. You can see that he stood on the shoulders of giants. There were lots of people that went before him. And so the contribution he made was absolutely wonderful, but we should never forget the work that other people have done prior to the work that he did in the 1950s and onwards. So this, there's a bit of, he began his work in French Equatorial Africa in the Congo. He was asked to estimate the grade of a 200,000 ton lot of low-grade lead ore. And then, so it became something he was faced with from his work, but it grew into a real interest. And perhaps one of the most important concepts that he really got to grips with was the idea of heterogeneity, because it lies at the root of all sampling errors. So, and this really is what this talk is about. It's about how to deal with these errors, how to identify them, how to cope with them, and how to ameliorate or get rid of them, eliminate them. Pierre Guy came up with this little formula which said that the heterogeneity carried by any fragment in a lot is equal to the mass fraction of the grade in the material minus the mass fraction of the lot divided by the mass fraction of the lot multiplied by the mass of the individual fragments divided by the individual fragments covered divided by the average of the mass of the fragments. And after a lot of work, he came up with this equation that we see at the bottom here, which Dominique Francois Bongasson then took and converted into this much more simplified kind of equation. This K coefficient includes a lot of variables. In fact, it includes these 4 variables down here, the mineralogical composition factor, the shape factor, the granulometry factor, and the liberation factor. So they're all included in this value for K, multiplied by the size of the nominal size of the fragments that you're dealing with, raised to, and this was Dominique's major contribution. Where before Pierre Guy had always used the cube term, Dominique said, no, let's calibrate the material and we'll find the correct alpha value for the material. And then, of course, it's divided by the mass of the sample. So this was a major contribution by Dominique Francois Bongasson. So the other things that Pierre Guy realized was that he was after what the minimum sample weight should be in order to achieve a necessary degree of reliability in his estimate of the error that might be associated, or the variability that might be associated with that material. So he wanted to create a systematic, mathematically based framework in which every error could be analyzed and explained. And he was going to use strict algebraic relationships, and he was looking for practical, implementable formulae. So the heterogeneity was his concept, lying at the root of all the sampling errors. He recognized that his models had universal validity, and its scale rather than physical state that differentiated between the range of applications. He then worked in 1962, he worked on chronostatistics and using the concept of the semi-variogram that had been proposed by Matheron and later Michel David. So he took this work and applied it for process streams. And then he also articulated this particular principle that each and every fragment must have the same statistical probability of being selected for a sample as every other fragment if you are going to have sampling correctness. So the only way that you can get representativity is to make sure that you've got a correct sample. And if you want to get a correct sample, you must follow this principle. He also did a lot of work on proportional sampling and bed blending as well. Okay, so let's just move on and look at, this is the range of people taking samples, sampling situations that you might be faced with. And what we want to do is we want to obtain a representative sample. So the only way you can obtain a representative sample is that it must be a correct sample. And in order to be a correct sample, each and every fragment must have the same statistical probability of being selected as every other fragment. So that's really the definition of a correct sample. And if the sample is correct, then it will be representative. And that's really what we're aiming for here. So a representative sample must be obtained in a probabilistic manner. All particles must have the same probability of being selected and extracted. And of course, it must preserve the physical and chemical properties of the lot that it's drawn from. So it must be composed of similar particles and in similar proportions. So there are a wide variety of methods to recover samples in the field, and I think this was alluded to by the presentation by Kathleen, for which I thank you. It was a very informative presentation. And she was just talking there about making sure that you've got the right equipment, containers, notebooks. You need to take economics, time, and access into sample to site into consideration. The target analyte may be invisible, so we must understand the heterogeneity of the materials, and that the materials are of different composition and constitution. We have solids, mixtures, slurries, and aggregates. So it's a wide selection of materials that we could be sampling. And the distribution of grain sizes must be similar. So, for example, if we're dealing with grain or food stuff, they will be more or less similar, but can be very different if we're looking at blasted materials in an open pit type operation. So size and access to the lots can vary widely. Just down here, there's some questions that I'd like you to think about. How much does one sample or one assay actually cost? You know, we submit samples for assay quite quickly. We don't really sort of think about it too much, but what does it actually cost? And then how many samples or assays does your company assay per day? And then what is the cost of one sample? And so what is it costing your company to do this sampling and assaying? And if it will be a substantial amount, we need to do it correctly. So more than just what is the cost of the sample, we need to ask ourselves, what is the value of the samples that we are taking on a daily basis? So the theory of sampling is a set of unifying principles that guide the way in which samples are taken. How easy is it to recover a representative sample? Well, it depends on things like the size of the lot, the size distribution of the particles in the lot, the internal heterogeneity of the lot, and a number of other things. So the number of increments to be combined to give a primary sample is a function of the material of the material heterogeneity and fragment size. So normally we don't just take a single sample from a lot in this particular situation like you see on the right here. It should be made up of a composite of a large number of samples. And in all of this, it's the representativity of the primary sample that carries most of the weight. So the primary sample must be representative, otherwise there's no point in processing the material. Even our best efforts after taking an incorrect primary sample are going to be generally a waste of time. So we must look at making sure that our samples, the primary sample in particular, is representative of the lot from which we are taking it. All right, in what follows now, we've got a series of concepts that I just want to bring to you. We talked about sampling in a very broad and general way. We talked about the equations that he produced. We talked about some of the things that he's found, some of the underlying principles. We've looked at sampling situations and places where sampling is taken. And now I want to just move on to some of the basic principles that are essential for taking a good sample. And the first of these is the data quality objectives process. Now, this was guidance for systematic claims using data quality objective process. It's there's a link here at the bottom that you can go to the Environmental Protection Agency, and they put this together because they realize that they're taking a lot of samples and they want to ensure that the reasons that they're taking the samples and the results of what they're going to do with those results are also clearly stated, and so that there's not a waste of money and there's a real focus on why they are taking the samples. So they've got a 7-step procedure here. First of all, you state the problem, you identify the decision that you're going to make as a result of obtaining a result. You're going to identify inputs to that decision. You will define the study boundaries. You will define the decision rule. You know that for every analysis, there's some sort of error associated with it. So you then must then specify the tolerable limits of the decision error. And then once done all this, you must then go back and optimize the design. So there's a huge amount of information that's embedded in this. And you will do yourself a big favor if you just go and look at this link and understand what these data quality objectives are all about and why they are important. It will really, it's absolutely crucial. Another concept that I just want to introduce here is this idea of lot dimensionality. So we have 0 dimensions, 1 dimension, 2 dimension, and 3 dimensions. And if you just consider a lot of dice, for example, let's say you've got 27 blocks in here. For 0-dimensional sampling, all the blocks are equally accessible and they equally you could make a choice of any 2 that you wanted to. So in this particular case, it's samples 3 and I think it was 26 here or something like that. But they're easily accessible. There's no restriction on accessibility. Then for a 3-dimensional lot, which we're looking at here, and here is a diagram underneath here, just showing a man taking a sample from a pile of chromite ore, or even a front-end loader taking a bucket load of material here. These are all 3-dimensional sampling situations where there's a block behind number 5, below block number 11, and to the left of block number 17 that is totally inaccessible. So there are portions of this lot that are inaccessible. It's a 3-dimensional lot. What we can do is we can define the lot in 2 dimensions and then sample across the 3rd dimension, as is the case, for example, when you do drilling in an open pit environment. So this is typically a 2-dimensional sampling lot. But what we would really like in every case is 1-dimensional sampling, because it upholds the principle that each and every fragment must have the same statistical probability of being selected as every other fragment. So anything that's on a moving conveyor belt, you can put either a cross-belt sampler or a belt-end sampler here, and this principle will be upheld. So what you need to think about is that, is there any way of moving our lot to a 1-dimensional lot? See, what it would mean in a case like this is that you relocate the stockpile to a different position, and in that relocation that you have some sort of sampling facility. Here are a variety of cross-stream cutters manufactured by ESSA. And so what happens is that this cutter blade here moves across the falling stream, and as it moves across the falling stream, it takes out a selection of material. And all of these uphold the idea that each and every fragment is going to have that same statistical opportunity of being in the sample. So this concept of the dimensionality of the sampling process is a very simple, but it's a very useful kind of concept. And one should try and in where possible ensure that you can reduce your flow of material to a stream that can be sampled in this way. All right, so we're moving on now. So those were just some basic concepts, the idea of data quality objectives and lot dimensionality that we will be talking about later on. But I just want to move on now to talking about the errors that Pierre Guy defined. And this was the contribution that Pierre Guy really made, is that he quantified and classified these errors. And he said that there are 7 sampling errors, Although we talk about 7 sampling errors, there are, in fact, probably 10 different errors now. Not that they were unnamed or unknown to Pierre Guy, but he did not actually include them as part of this. So there are, to start with, the so-called correct sampling errors and the incorrect sampling errors. And the correct sampling errors include the fundamental sampling error and the grouping and segregation error. These are random errors arising from constitutional and distributional heterogeneity of the material, and they can affect the sampling variance if they're not controlled. So those we refer to as the correct sampling errors. There are also incorrect sampling errors, and we refer to these as the extraction error, the delimitation error, the preparation error, and the weighting error. These are non-random errors arising from poor mechanical design and incorrect installation, incorrect sample preparation and fraud, and they affect both sampling bias and the variance if they're not eliminated. So these correct sampling errors are, in a sense, true errors, whereas the incorrect sampling errors are actually biases. And that the total sampling error is a combination of the correct sampling errors, the incorrect sampling errors, and the analytical error. And I'm not going to go into much detail about the analytical error because that's the area of the assay lab. So here's just a template for understanding these sampling errors. So the random errors are based on material heterogeneity. I talk here about the in situ nugget effect. Now, this was an error that Francis Pittard proposed. There are not that many people that agree with this particular type of error, but I thought I must include it just to do him service. And then there's the fundamental sampling error that we talked about, the grouping and segregation error as well. So, but then at the bottom here, we've got the periodic quality fluctuations and long-range quality fluctuations. These two groups of errors, these two, QE1 and QE2, refer specifically to the errors generated on a conveyor belt and require the use of a variogram to really understand what's happening there. And we will look at that in some measure later on. Then the non-random errors due to mechanical material bias include the increment delimitation, increment extraction, increment weighting, and increment preparation errors. And then finally, the analytical error itself. Okay. So I wanted to just talk here about heterogeneity because there's so-called constitutional heterogeneity, which is due to grain size distribution of particulate matter, the shape of the particles, the concentration of the analyte, its density and bonds, physical and chemical, with the matrix particles. So it's caused by differences in the chemical composition and physical properties of each particle. So it's the constitutional heterogeneity. It's the way the particles are actually made up. The distributional heterogeneity, however, is due to the effect of gravity on the segregation of particles. So it's principally as a result of gravity, but it can be also occur due to differences in particle size and moisture, and it can affect the spatial distribution of the particles inside the lot of the particulate matter. So heterogeneity describes the uniformity with which the target analyte is distributed through the lot. It's the main contributor to uncertainty associated with sampling. So these constitutional heterogeneity and distributional heterogeneity are really, really important because uncertainty is embedded in any sampling result or average of such sampling results. So what I'm going to do now is I'm going to look at these 7 errors that Pierre Guy defined. So we'll start off with this fundamental sampling error. That's the smallest possible error, and it's given by, this was the equation that Pierre Guy defined, and then this was the equation that Dominique Francois Bongasson modified it to, which is fine. They are in total agreement with that, and this is a very popular equation these days and very useful, very powerful. But the fundamental sampling error is minimized by reducing the fragment size or by comminution in the lot, or increasing the sample mass. So just look at this. This here is it's a variance. It's the variance of the fundamental sampling error. And it's equal to K, this coefficient, multiplied by the fragment size to raise to this power and divided by the mass. So if I decrease the fragment size, I'm going to decrease this error. If I increase the sample size, I'm going to decrease this error as well. So I just feel those are important relationships that you should see. So the fundamental sampling error is due to compositional differences between the fragments, the constitutional heterogeneity of the lot. And here is another equation produced by Piaget, which is just for the constitutional heterogeneity. So what are the things that, how do we characterize the sample heterogeneity? The heterogeneity is so important. How do we get a grasp of it? What can we do to actually lay hold of this fundamental sampling error and understand it? Well, there are 4 types of heterogeneity tests or calibration. The first is the replication experiment, and this is specifically for 3-dimensional lots. So, this may allay your fears concerning the fact that you have to deal with 3-dimensional lots. If you need to deal with 3-dimensional lots, if you're forced into sampling 3-dimensional lots, make sure that you understand what's needed in this by this replication experiment. So that's the first way. The next is the duplicate sampling analysis method, which Dominique Francois Bongasson created. There's the segregation-free analysis method, which is a method that I designed principally to try and get rid of the segregation that seemed to dog these tests. And then there's the standard heterogeneity test designed by Piaget himself. So there are methods of laying hold of this fundamental sampling error and understanding what it's all about. So what are we trying to do when we do a heterogeneity test? In each case, we want to be able to determine the parameters for it all, the sampling characteristics that will allow us to compile a nomogram. So the nomogram is where we headed with this. We want to be able to compile a nomogram. What does the nomogram tell us? It tells us how to reduce the mass and how to reduce the fragment size in order that we minimize this fundamental sampling error. So that's really why we want to do these heterogeneity tests. That's the aim and the logic behind the heterogeneity tests. Okay, just to summarize, or not to summarize, but to tell you a bit about the replication experiment, and this is a very, it's a trimmed down version of it. So sampling any particulate lot will include a primary sample, a secondary sample, and maybe a tertiary sample. Okay, so there are maybe more stages depending on the nature of the material. So you take a primary sample, but you're not going to send that primary sample to the assay lab. You've probably got to crush it and split it before you get it to the stage where you can put it in a pulverizer and derive an aliquot for analysis. So at each stage, from the primary to the through the secondary to the tertiary sample, there will be various sampling and analytical errors. Then the replication experiment means repeating the sampling procedure at least 10 times. Well, people say 10 times. Really, you need it about 30 times. You know, if you want to get a really nice stable variance, you need 30 of these analyses. The most important thing is that the procedure must be repeated identically. So you can't change it from the protocol from one sampling event to the next. You must do exactly the same thing. And then all sampling and analytical errors are then embedded in the variance of these analytical results, 10 to 30, preferably 30. And you're then in a position to calculate the relative sampling variability, which is simply the standard deviation divided by the mean of those analytical results. And this gives you this RSV in percent. So you are looking for the lowest RSV that you can derive. And if there's some other method of sampling that gives you a lower RSV, then select that method as the appropriate one. All right, so we would start off, let's just look at the progression here. We start off with a stockpile. Maybe you're going to sample that stockpile using a front-end loader. You're going to spread the material out. You're going to select some samples. Those samples are then taken to a laboratory where they are crushed and split. You may use a rotary splitter. Here's a nice example of a rotary splitter. And then finally, once you split that and pulverize this material, you will then select an aliquot, a single aliquot that you will present to the analytical procedure or the analytical instrument. So it's just important to see that there are errors at each stage. So there's a primary sampling error. There's a secondary sampling error. There's a tertiary sampling error. There may be quaternary sampling errors. There may be analytical sampling errors, but all of these are then combined to give you the overall error of this whole sampling process, because we've gone from this lot down to this photometric method of assay. And there are errors all along the way, and we want to make sure that we understand how they are accumulated. So it's essential that the process is repeated identically for every sample. Yes, we've said that. In this way, each sample will pick up whatever sampling variance is introduced along the way. So we start off with the primary sampling. We repeat the replication at any of these levels. So then we do the secondary sampling. We then do tertiary sampling, and then finally at the analytical stage, we also have some sort of error. I just want to assure you that the whole idea of replicate sampling is not the same as measuring duplicate analyses in the laboratory, which is a QA/QC process. So it's a progression here from the lot or stockpile to the aliquot. Here is a picture of what the Canadian Grain Commission do in terms of the way that they sample their grain. So they take out these increments from each of the samples. So they've got 3 increments as a result of, or 3 composite samples as a result of incrementing these 5 samples for each. They then combine all 3 composite samples into a single sample and then split it into 4 individual samples, and which they then assay. And I just want to leave you with this question. What is it that they could have done differently? What is it that they could have done differently? And you know, if they had just taken the time to ensure that instead of the one-dimensional sample or the 3-dimensional sampling that they're doing from this truck, that they put all the grain into a stockpile and convert it to a one-dimensional stockpile, and then do incremental sampling from that flowing conveyor belt. And they would have come up with something, I think, that might have been a bit better. Okay. First of all, the replication experiment. So we're looking for a threshold, an RSV threshold for a given sampling protocol of a particular lot. and it's established by the user as a quality index of the sampling process. That's all that this RSV does, this relative sampling variance. It's a quality index. So you are the one that chooses what that index should be. If 20% is acceptable, well, then that's fine. But if it's not, if 20% is not acceptable, you must then make a decision about what percentage you actually want. So maybe it's going to be 10% or 1%, but you must make that kind of decision. It provides no estimate of the magnitude of the sampling bias, so you must eliminate all those biases before the experiment. It's the combination of the total sampling error and the total analytical error. It's again, I just repeat this, it's a quality index. Yeah, okay, so the RSV quantifies different sampling procedures for the same lot, and it quantifies the heterogeneity of different lots for the same sampling procedure. Okay. So this was the replication experiment. I just wanted to point out the duplicate sampling analysis method. This was the work that Dominique did. And as I say, he took the equation that Pierre Guy came up with, modified it slightly, and then came up with his approach to establishing this fundamental sampling error. What we should just notice, I think this may be repetition, is that the fundamental sampling error is proportional to this fragment size and inversely proportional to the mass. You cannot escape this. There's no, it's not like you can eliminate this. It's better that you understand what it is so that you can compile a nomogram, but there is no escape from it. So what Bongason did is he changed the format of this equation. He took the logarithms of both sides, and this is simply a straight line equation where you've got y, which is this here, equals mx, the ln d is the x, plus c, ln k. And now you can control for the variance and the mass by taking samples. You can control the fragment size, and what you want then is the slope of that line and the intercept on the axis. So here's the experimental procedure. You take 40 kilograms of material. It can be up to 300 kilograms, depending on the nature of the material that you want to do this experiment for. And then you reduce the lot to 95% passing 1.9 centimeters in the jaw crusher. Split out 10 kilograms. So you've got now, you'll have 10 kilograms at 95% passing 1.9. Recombine and crush the remaining 30 kilograms to 1.2. Take out 10 kilograms of that. Recombine and crush the remaining 20 kilograms, give you 95% passing 0.63. And then you split out the third quarter, then recombine and crush the fourth quarter down to, say, 0.1 centimeters. So at the end of the day, you end up with 4 series of material, 10 kilograms each, 95% passing these sizes, 1.9, 1.2, 0.63, and 0.1. You don't have to use these exact sizes. You can use different sizes, but make sure that there's enough space between those sizes. And then you take those series, those 10 kilograms, and split each of those series using a rotary splitter or a riffle splitter, which is my preference, into 32 samples. So in this way, you end up, okay, this I did with 75 kilograms of ore, and I split it into 6 series of different sizes, but it doesn't matter. And then you split it using a riffle splitter into these 32 samples. Those 32 samples you're going to submit for assay. You're going to get the results back, and you do some basic descriptive statistics. Just look at this. Here's the average sample mass, 214, 216, 201, 219. Not much difference. Here's the analytical variance. It's identical for all of them. Here's the average grade for these samples, 12.34, 12.5, 12.65, 12.8. Not much change here, but look at the variance. The variance here is 13.5, 7.59, 3.38, and 0.84. So there's a massive change in variance, very little change in the average grade. So what you do then is you do the necessary statistical results of these assays, which I'm not going to go through in detail here. And remember, we converted that equation into log space. So you use the log of the fragment size and the log of the variance times the sample mass, and you come up with a straight line, and you can just estimate from the straight line the slope and the intercept on the y-axis. So here's the y-axis at 0. Here's the intercept, which is 4.6325. Remember that during log space, so you've got to back transform it into normal space, which gives you about 105. But here's the slope, 1.0505. So that's the slope of this line for these experimental data. Okay, and then from that, using K, so you've got, let me just go back here, you've got a value for K, that's this 4.6325 converted, back transform, and you've got a slope. You've got this alpha, the value for alpha here. So in using these values for K and for alpha, you can then take the logarithms of both sides, transform this equation, and then you can compile a sampling nomogram from this. Here's the slope. Okay, in this case, I used 1.7. And if you back transform that 4.63, you get about 103. This was for a mesothermal porphyry copper gold deposit, which is mining about 1.8 million tons a year. So their daily production is about 5,000 tons. We can convert that to grams. And then we know that there are so many grams per shift because they have an 8-hour, they have a 3-day shift, 3 shifts per day. And as a result of that, we can determine the amount of number of grams that they're mining in a shift. And so that's about 17, what's that, 17, it's about 17 billion, 1.7 billion grams that they're sampling in a shift. The top fragment size to start with is 50 centimeters. Then you would put that through a primary crusher. That goes to 2.5 centimeters, same amount of material. But at this stage here, you split it down to 600 kilograms. At 2.54, you then crush that down to 1.2. You've still got the 600 kilograms. Then you split off 10 kilograms at 1.2, crush that to 0.5, and so on, until you get down to your 50-gram aliquot, which is at 106 microns. And you are then able to take that data, this information, from that you calculate this relative variance using Guy's formula, or using the formula by Dominique Francois Bongarçon, and you come up with the nomogram. So here's the nomogram for that particular ore. Okay, and what is this telling you? It's telling you that this is the material that's delivered from the mine. You crush it down to this level here. You're changing the fundamental sampling error. You then split it to this level here, crush it again, then you split it again to this level number E, and crush it down to F, then split it off, it gives you the point G, then you crush it again, and then you can split off your 50 gram aliquot. What you should not want to do, of course, is to breach the safety line, which you do in 2 places here, but then you can go back and adjust the nomogram so that you do not breach the safety line. And at the end of the day, you can come up with a result for the total incremental variance for that sampling process. And in this particular case, it's 12.6%. What is interesting is that, it's the precision, this is the variance. What is interesting is that you can calculate this precision before you ever take the sample. So this is all the sort of theoretical work that precedes that. All right, so we've talked about what have we talked about in this last section? We've talked about the fundamental sampling error. That's all we've talked about at this stage. We've just talked about the fundamental sampling error, how to get a grip on it, how to get a grasp on it. We now want to talk about the grouping and segregation error. So it's not a material constant. It depends on the fact that groups or fragments group and segregate locally in space and time. So when you see a shoal of fish, there's no actual connecting link between these fish. The only commonality is the fact that they are all of the same species. They tend to group together. Here you see, so that's in an aquarium or under the sea. Here's what's known as a murmuration of birds just before they settle at night. They tend to group in these flocks of birds. You want to know, here we can see a high density grouping, but in this area here, there are no birds at all. So it's like a grouping and segregation that's taken place there. So this, when we look at a stockpile in which the materials have segregated out, we see this is how do you sample this? Very difficult. You know, you've got very fine material here, very coarse material here. One of the methods, of course, is to use a spear. This may be a better way. And here's the stockpile that they're building, that they want to then go and sample. It would be far better if somewhere on the conveyor belt that's conveying this material to the stockpile to actually insert a cross-belt sampler or cross-stream sampler that will allow them to take the samples rather than using this ISO standard sampler, which really cannot give you an effective sample for this lot, with due respect. Okay. This is just showing more about the grouping and segregation error. This here in the bottom is known as the Brazil nut effect. If you've got a ball of different size, the density is not that important, in fact, but it's the size that makes a lot of difference. And you add vibration into this container, you'll find that this ball that started off at the bottom ends up on the top. So the next time you get a box of nuts and you want to go for the Brazil nuts, just take the box of nuts and shake it, and your Brazil nuts will end up on the top. Okay, so now we have dealt with the fundamental sampling error. We've dealt with the grouping and segregation error. Let's look at this group that we call the incorrect sampling errors. So the previous two were the correct sampling errors. These are the incorrect sampling errors. We've spoken about them already. We've said the increment delimitation error, the extraction error, the preparation error, and there is the weighting error as well. But these errors are bias generating errors. And they are biases because they interact. The bias is manifest where the sampling tool actually interacts with the material that you actually want to sample. So that's where the bias is introduced. So there's, first of all, the increment delimitation error. These three shown in green here are correct delimitation. These two are incorrect delimitation. Taking a single part of the stream all of the time is incorrect delimitation, and taking part of the stream part of the time is also incorrect delimitation. What you need is to take a sample across the stream. It can be in that form, or that form, doesn't matter. but you want to take in the entire stream part of the time. This just talks more about the increment extraction error. I'm not going to go into any detail there. The increment preparation error is simply due to contamination, material losses, chemical and physical alteration, human errors, ignorance about preparation processes, or illegal activities such as fraud. And I'm not going to go into that in detail. You can find all that detail elsewhere. Okay, then we'll go on to the increment weighting error. So this occurs when the increment masses are not proportional to the mass of the material they actually represent. So this can be a real problem in time-based sampling, and it's caused by rapid variations in the stream flow rate or the amount of material that's actually on the conveyor belt. If it was just simply a continuous, nicely organized stream instead of the lumps and bumps that usually occur on a conveyor belt, all well and good, but it's generally not. So this increment weighting error is an error that is introduced. We can reduce that by regulating the flow rate or using a variable speed divider in conjunction with a weightometer. I just included this picture of this beautiful resin splitter. Very, very nice. And yeah, here's another splitter or cutter through a sample stream. The analytical error is the domain of the assay laboratory, and I'm not going to worry about that too much. What I did want to just show you is the issues regarding error and bias. So here is a set of data with a 1% error but 0 bias. I increased that to 5% error and 0 bias, and 10% error and 0 bias. So all you can see here is that this cloud of points is expanding, but there's no actual shift in the data to the left or the right. In this particular case, we have this is for coal data. Here you can see that the error has increased by 10%, but there's no bias. Whereas at the bottom here, we've got a 0.9 times multiplicative bias and a 1.1 times multiplicative bias. So that's what I wanted to just show you about understanding the difference between error and bias. Okay. The reason that I just put this in is that the discovery of DNA was a huge step forward in understanding how our genetic makeup is controlled. So it doesn't matter whether you go to a hair on your head or a piece of your toenail, it will contain the same DNA. And this DNA describes exactly who you are and all your characteristics of yourself as an individual. The important thing here is that ores and minerals carry no DNA. And so what we've got to do is try and build a material's DNA. And so we start off with a primary sample, we move to secondary and tertiary samples. And the theory of sampling aims to set up procedures and protocols that will lead us from the lot to the aliquot, but preserving all the essential characteristics of the lot in the process. So at the end of it, hopefully we have built a material's DNA. So that's really what the theory of sampling is all about, and what it means to take a representative sample. So how are we going to address the foundations here for overcoming the sampling errors? Can I just say at this stage, Nicole, that I'm way over time already. I've spoken for just over an hour, and I'm just a bit concerned that we're not really going to get through all this. So I'm not really sure what to do. Yeah.
I'm happy. You would have seen I allowed quite a bit of time sort of for breaks. And I think we do finish quite early this afternoon. So I'm happy if you want to continue, and we can just push the breaks out a bit, if that's okay.
That's
If
okay.
you're happy
Thank
to
you.
continue.
Yeah, okay, thank you
Cool.
so much. I appreciate it, and I do apologize, folks, for the fact that I've just taken too much time, but it is such a huge subject, and I'm trying to, I thought I was trying to do it justice, but anyway, let's just press on. Okay, so we want to have a foundation for addressing and overcoming these sampling errors, and that is what the theory of sampling does for us. But we have got 6 governing principles that we just want to look at. And the first of those is the fundamental sampling principle. Now, the fundamental sampling principle, and okay, so let me just name them. So it's the fundamental sampling principle, the sampling scale invariance, sampling correctness and bias-free sampling, the principle of sampling simplicity, the lot dimensionality transformation, which we've spoken a fair amount about, and lot heterogeneity characterization, the use of variography. So we haven't looked at that yet, but I'm hoping that we will be able to. So here are these 6 fundamental principles, and we must obey those, and we're going to look at them in some detail. Then there is this full spectrum of sampling errors that we just named can be mitigated by 4 sampling unit operations. And they include, first of all, composite sampling, comminution, making sure that the fragment size is reduced, the mixing and blending of the material, and representative mass reduction. So these, whether you're at step 1 or step 4, these sampling unit operations must be carried out at each step of the process. So how do we achieve representativity? So that there's no inherent feature or characteristic in a sample that allows us to classify it as representative representative or not. So when your sample reaches the laboratory, there's no red or green flag that says I'm a good sample or I'm a bad sample. The only way to ensure a representativity is to document the history of the processes and procedures used to produce that aliquot. If the process delivering the aliquot is correct, then it'll be representative. But if the sample is incorrect, it can never be representative. So one might ask, what are the criteria for representativity? So it depends on the sampling method, the physical extraction, the extent to which constitutional and distributional heterogeneities are accounted for. But this diagram here is a modification of a diagram that Kim S. Benson compiled. And you have to start from these foundations here. Whether you're dealing with a primary, secondary, tertiary, aliquot preparation, or the analysis, these foundational principles must be in place. You then have your 4 sampling unit operations, which must be implemented at each stage. And then you've got the fundamental sampling error, the grouping and segregation error, process trend error, process periodic error. Now, those errors only tend to occur during primary sampling. So that's important, and they occur on the conveyor belt. Once you've extracted that primary sample, you then into the secondary, tertiary, or aliquot preparation stage. Okay, so let's look at these. So the guarantee to representativity is accuracy, precision, correctness. So priority 1 is to minimize the sampling error through the methods that we talked about, making sure that you understand the material characteristics, you can use, and understanding the relative sampling error for the lowest value of precision. So that is first, those were all the methods for characterizing your material that we talked about. And then priority 2 is to eliminate sampling bias through correct engineering of the equipment. So there's sampling errors and sampling bias, and these are conveyor belt characteristics that, that need to be attended to. So these priorities apply at every stage in the process. And the processes and caveats are the same at every stage. So it's scale invariant. It doesn't matter what scale you're talking about, whether you're in the laboratory or the conveyor belt, you must make sure that you are obeying these principles. So here are the foundational principles. Again, it's just each and every fragment must have the same as each and every other fragment of being in the sample. So this is the fundamental sampling principle. The sample scale invariance says that it doesn't matter at what scale you're dealing with, whether it's the primary sample or down in the laboratory, the same principles apply. It is scale invariant. So you must make sure that you apply all the methods of mitigating these samples. That's the sampling unit operations at every stage of the process. Then there's the principle of sampling correctness, which means that the aliquot is presented for analysis is representative of the lot. And we said again that you know, it's based on this principle that each and every fragment must have the same opportunity as every other fragment of being in the sample. So that is the principle of sampling correctness. If the sample obeys this principle, it will be correct. If it is correct, it will be representative. And then the principle of sampling simplicity. There are a number of principles, and these principles are repeated again and again and again. It doesn't matter whether you're at the primary, secondary, tertiary, or analytical stage, the same principles will apply. Then there's lot heterogeneity characterization. We've been through that. We talked about the heterogeneity tests. We'll also look at variography a bit later on. Then there's the lot dimensionality reduction. And we've spoken about that. Try to make sure that you are sampling in a one-dimensional sampling situation. Here are the 4 sampling unit operations. So this is, first of all, is composite sampling. Make sure that your sample is made up of several increments where possible. Make the sample up, and you're far better off taking a composite sample made up of increments than you are of if you just take a single sample. So use composite sampling, it's essential. Then crushing and comminution. Reduce the fragment size as far as possible for your given mass, all right? So that's really, really crucial. I put this diagram in here just to show you the way that the log of the sample variance varies with the fragment size. You can see here that the mean grade remains almost constant. So there's no change in the mean grade, irrespective of the fragment size. It doesn't change, but the sample variance changes dramatically. And this is what we use to get a handle on the fundamental sampling error. So this is essentially that fundamental sampling error issue. Okay, the third of the 4 sampling unit operations is to mix and blend. Here we have a rotary V blender. And what does it try to do? It tries to minimize the grouping and segregation error. And then there's so that's what this V blender is doing, mixing and blending. And then there's representative mass reduction. Now, I've just spent 2 weeks in Australia looking at various splitters and so on. And one of the things that I am a real fan of is the Ripple splitter. This is a representative mass reduction device. It should be next to every reverse circulation and blast holes drilling rig in order to take, if you're going to be taking samples that way from those rigs, then make sure that you're using a riffle splitter in the field. Make sure that it's big enough to manage that, because this is going to give you representative sample reduction. Okay, I'm not going to talk about that. What is the theory of sampling? Okay, just to sort of, yeah. So the theory of sampling is built on 6 governing principles, which we looked at, and 4 sampling unit operations that are applied in a systematic fashion to all processes, procedures, and equipment. It's a framework. The theory of sampling is a framework, and built on evaluating common problems and features for different sampling, for different lots of different sizes in different sampling settings, to guarantee accuracy and precision, as well as correctness and representativity as we move from the lot to the aliquot. So at every stage in the procedure, sampling errors and bias stand by. They are ready to corrupt the sample by introducing misinformation. And so this is what the theory of sampling does. We're constantly in a defense mode against these errors and bias. So at every stage, the lot is moving towards is moving or stationary. The theory of sampling provides the principles, practices, and procedures to eliminate the sampling bias and minimize the sampling error. The sampling nomogram we've just looked at is a really important and crucial bit of information that tells you when to crush and when to split, making sure all the time that you stay below that the safety line, the safety limit. Okay, yeah. So remember that your decisions are only as good as your samples. This is either Patricia Smith and Francis Pittard is considered to have said these things. Just remember that it's built on the 6 governing principles and 4 sample unit operations. I think we've been through this enough now. I think we've been through that. We've been through that. What I just wanted to do is I want to get down to this position here where we talk about the primary sampling. Okay, here's in a 3D lot, a 2D lot situation, and a 1D lot. And these are places where you're going to recover your primary sample. And so in each case, you need to remember what the principal sampling foundations are, and then the sampling unit operations, making sure that you're taking composite samples, crushing and comminuting, mixing and blending, and then splitting in a representative way to produce the first subsample. From that, we go to the secondary sample. Here's the secondary sample. So you've done some activity on that material, you produced a secondary sample. Then we're going to do some further either compositing or separation or using a crossbelt cutter to produce a third subsample. And then you're going to move to the laboratory where they will do crushing, mixing, splitting to produce a 4th subsample, which then is then split in the right way to go to a pulverizer, and you put it either in an LM2 or LM5 pulverizer. You can do screen grain size checking and particle size distribution, and then you, from these powders, you produce the aliquot for analysis. Okay, so yeah, I'm not going to go through that. I just want to go to here where this is just shows the emphasizes the importance of the primary sample. We've seen this diagram before, but here is an equation that shows you how the total error, which in this case is 20.59%, is calculated from each one of these subsampling stages, from the primary all the way down to the tertiary and finally to the aliquot. Now, you'll notice here that I've got a red line that says this is the domain of the theory of sampling. This is the domain of measurement uncertainty. It's something that I can't go into now, but you should just keep that in mind and prick up your ears if you come across that in future. I did want to just look at the variogram and data variability in processing streams. So this is a set of data, and really you can't tell too much from this data just as it is. This shows the analytical concentration versus the increment number, and this shows the heterogeneity contribution versus the increment number. But if you plot a variogram of these data, there are really some very important points that emerge. So this is known as the nugget effect in geostatistical parlance, and is referred to as V0. And so let me just move on to this one here. So this is V0, or the nugget effect. This is the process variation. So you can see between the first sample and the difference between the nugget effect and the first sample is this process variation. And it describes all the variability in your plant and process as a result of your sampling. Then you can identify periodicity in this particular diagram, in this variogram. And so it will tell you, first of all, what is the period of these of this variability, of the cyclical variability, and it will tell you the amplitude of the cyclical variability. And this is information that you get from a variogram that you cannot get any other way. And that's why the variogram is so important. So this is your estimated total sampling error. This is the lag, or the interval between samples, and this is the number of increments that you are using to take that sample. And this type of diagram here is an extremely useful and valuable way to find out, what kind of lag interval you should be using, how many increments should you be taking in order to obtain the best estimate of the total sampling error and the analytical error. The important thing is that this information that you derive from the variogram must be taken back to the variability plot. The only way that you can get these data that speak to you and tell you about the importance of various limits to your sampling data is by the use of the variogram. And there will be upper and lower specification limits and so on. And if you have signed a contract with your supplier or with your customer, and you see that your process is just not able to reach the specification limits that are defined in the contract, you better go back to your customer and ask him to renegotiate those results. Otherwise, you are always going to be missing out and losing out because your process just is not capable of producing the results that you're expecting. And the only way to know about that is through this variogram. So it's something that's really powerful. Okay, just in summary, your sampling is about representative mass reduction, but you can't do that until you minimize the sampling error, which comes through an understanding of heterogeneity and material characteristics. You can't do that until the equipment is correctly designed and eliminates sampling bias, which deals with equipment characteristics. So in summary, your sampling depends on your understanding of the principles, practices, and procedures of sampling, the correct sampling equipment, the correct application and use of the equipment, and you must work your way through a multi-stage scale invariance system, irrespective of the sample or the subsample mass. Otherwise, there's no way that you're ever going to achieve a representative sample. Okay, folks, thank you very much. Thank you for listening. I do apologize for taking over too much time, but it's a huge subject. I just didn't know quite how to manage it, but I'm willing to answer any questions that anybody may have. Thank you, Nicole.
Thank you so much, Dick. Really appreciate it. Really informative. And as you say, it's difficult to squeeze all of that into an hour. So I'm glad we were able to give you a bit more time at least.
Appreciate it.
Does anybody have any questions?
How do we ask a question?
Go ahead, Grant.
How's it, Dick? Thank you very much. Very interesting talk, Grant Hayward here.
Hi, Grant.
All quite complicated stuff and all those formulas and funny things. I mean, I've seen some examples where, and this is where I as an exploration geologist, people have just done the bad sampling first principles in sampling the primary sample.
Yeah.
Certain instances with RC rigs having a fancy splitter that does the splitting for you and avoids the riffle splitter and gives you an A and a B sample. I found that that's been very inaccurate and failed a few times and compromised quite a few of my projects. So I never use that cyclone. I always use a riffle splitter, although it's a lot more work. It's proved to be, for me anyway, a lot more accurate. And then I've seen the case where people are trying to sample friable material, core particularly that's been drilled, that you can't cut with a diamond core or half core it. And they use a kind of a knife and chisel and try and get a half core sample. And in those instances, my strategy is to sample the entire core, although some people don't like that because you don't have any record left. But it takes away that problem of people coming back and questioning your sampling, your primary sampling technique.
Yeah.
So I think there's some very basic first principles that almost needs to be discussed for the guys that are almost not on the level of understanding all the complex equations.
Yeah. Look, Grant, I hear what you're saying, and thank you for using a riffle splitter. I tell you, the riffle splitter, I think the riffle splitter is the most underrated piece of sampling equipment there is. It is absolutely fantastic. It does a great job. If it's used properly, it really does a good piece of work. So we faced in lots of cases, people are saying, you know what, my company will never put in this equipment. It's far too expensive. They're not going to retrofit. You know, what do I do? The thing is that replication experiment is quite a useful way of taking samples. And I agree with you wholeheartedly. You know, if you can't split the core and it's very friable and so on, just use the whole lot and do your assaying on that. It may mean that they want to later on drill another borehole or whatever. But one of the principles that I usually say to people is, yes, your company is not going to spend that money. It is going to be difficult to take those samples, but this is it. You do the best with what you've got. And I know that it sounds a bit simplistic and so on, but very often that's what you have to do. You have to do the best with what you've got. You should try and, you know, particularly where there is a company, and it's difficult, very difficult in the exploration stage. Once the company has a plant or some sort of system going, you should, or prior to the actual installation or construction of the plant, make sure that there is sampling facilities that are included in that budget. You must include that in the budget. Somehow or another, you just got to make sure that they're prepared to spend the money and let you put those sampling facilities in. Otherwise, all I can say is, again, you do the best with what you've got. Wow.
Yeah, thanks, Dick.
We've heard about the importance of sampling and SG, and today I will discuss with you how data, and I'm quite sure that we will be hearing from other people, how data can be used or visualized. So today I would like to talk about industry best practice when it comes to gathering and storing your data to make the life of the QP easier when it comes to reporting season. So first of all, we're going just to look at some roles when it comes to data and data management, and then we're going to look at governance versus compliance, and then stepping into some best practices. And then if you have any questions after that, please do. Please note that I cannot see the participants, so if there are any questions during the presentation, I won't be able to see if anybody raises their hands. This is due to the way that the screen has been shared. Okay, so I love this quote: data that is loved tends to survive. So when we leave our tertiary studies, we really have no idea what really happens in production or work environment. We are qualified as geologists or geohydrologists or geotechnicians, and then we are placed in charge of data. And this tends to fall a bit more in the realm of IT or IM. So I would like to just give a quick overview of the different roles that's associated within the data and data management space. So when we look at data entry and database capture, these are both combination of getting data into a system. Data entry tends to be more of a manual input, but data capture tends to involve more technology and less of a human interface. So data capture technologies may include machine learning, robotic process information or RPA, as well as OCR or optical character recognition. So data entry can also include data capture. Then people tend to use these two roles interchangeably when it's actually not. We have a database manager and a data manager. So in this case, let's look at data as the vehicle. The database manager will be the mechanic and the data manager will be the driver. So a data manager understands the business and the mission of the company, the programs and services within the company, and also how other members of the company use the services and programs. Most importantly, the data manager understands how data can be used downstream and to facilitate more effective decision-making. So the data manager understands how to use the data to get the company to where it wants to go. So the data manager can drive the vehicle. A database manager is like the mechanic of the vehicle. It's knowing which tools and technologies are available to make the database more effective. So effectively extracting the data, or how to integrate the systems, or how to best manage the data within the database. The data manager understands the business of the company, but does not necessarily need to know the mission or the business statement of the company. So they don't need know how the data is used downstream. So if we look at it, the data manager knows the nuts and bolts of the database software, knows the industry best practice for database management, as well as access to the data for pertinent members. The data manager understands how that data is then used within the company and to align the use of the data to reach the company's business objectives. It's very rare that you can find a person that is skilled in both these, but you do find them. This leads us to data governance. Data governance is a subset of data management. Data governance is a set of policies and procedures that are used to ensure that data is managed in such a way that it can be trusted. In short, data governance ensures that data can add to the bottom line of the business by mitigating the risk of poor data practice and quality. So data governance is made up of different functions. When implemented correctly, it will lead to improved data availability, better data integrity, excellent data quality, your data security, which will then all lead to excellent data usability. So when working with larger corporations, there's a need to ensure that the data management system integrates well with greater IM systems. So in other words, what we're saying is Data governance will make sure that when you choose a solution that will house your data, that solution will integrate well with other systems within your IT infrastructure, because it's no use to have a place to store the data, but nobody can get to the data. So this will form part of your data governance framework to ensure that the future compatibility and continued agility of that system integrates well with your IT chosen systems. This now brings us to what is the difference between governance and compliance. I know a lot of you are probably wondering why we're discussing this, but as we progress, we'll see how this slots in nicely with our reporting and what's needed downstream, and how governance and compliance is actually now being a greater focus within the way that data gets managed, especially as we move from on-premises solutions to cloud-based solutions and the advent of all of the new systems that one can use nowadays. So governance helps you to act in the best interest of the business, which will improve the performance of the business, as governance sets the tone for the company's attitude to risk, ethics, and business practice. Whereas compliance embodies the business attitude in relation to the specific law and regulation, which in turn protects your company's reputational risk. So both of these will help your business to become more stable and productive. So if we look at governance, governance sets the tone for your company's attitude to risk. It focuses on the long-term performance of your company. It will influence the decisions like your service providers or your vendors or your users downstream or upstream. It's set from internal resources. So governance is something that will be decided by your executives, the board, or alternative internal stakeholders. And consequences of overstepping your governance will be a disciplinary or a dismissal if that governance set of rules is not followed. However, compliance is set from external resources, as it is normally set by the bounds of specific legal implications or laws or regulations. And that forces your company to stay within the confines of the law. And for overstepping compliance issues or breaking the laws, you will have legal actions or fines or penalties. Which brings us to this very nice fact that I love. It's not everything that can be counted counts, and not everything that counts can be counted. Because that sums governance and compliance up so nicely, because what you think might be an important part of your company's data might not fall within the compliance laws of an area, or you might think it's got nothing to do with anything. For instance, when you look at sampling data for wells, however, it may have a greater impact on your compliance that you might realize at that time. So this brings us to best practices. Firstly, why is there a focus on best practice? So let's look at one of the most major gold mining scandals in the 90s. I'm quite sure a lot of you are quite familiar with the Bre-X Minerals Limited scandal. For those of you that aren't, so Bre-X Minerals Limited bought a Busang mining site in Indonesia in March of 1993. And in October of 1995, they reported significant amounts of gold that was found in that deposition. That changed their penny stock. So penny stock is anything that trades for less than $1. And that made that their penny stock shot up to 286 plus Canadian dollars per stock. And that led to a capitalization of over 6 billion Canadian dollars. So the encouraging gold values reported and received a positive technical assessment from a consulting firm known as Kilborn Engineering. However, the crushed core samples had been falsified by salting with gold. So salting of samples is adding a valuable metal to the mine sample to change the assay value of that sample. And this is specifically done to deceive potential buyers of mines or investors. And in this case, it was added to the crushed core samples, and that added to the most elaborate fraud in the history of mining. So in the wake of Bre-X, what happened? So there was a number of lawsuits and angry investors, and this ultimately resulted in the Bre-X being bankrupt. There was a dramatic trial and some mysterious deaths and a Hollywood movie. So if you ever do get time and you're not familiar with it, please do go and read on it. It's very interesting. It was also proven that the samples were enriched by shavings from gold jewelry. However, it was never found at which stage these shavings were added. So this resulted then in the National Instrument 43101, or as we all know it, the NI 43101, for reporting to protect investors from unsubstantiated mineral project disclosures. So that then resulted in other best practice standards for disclosure as well. Some of the ones that you might be familiar with, which is NI 43101, your SAMREC, the South African Mineral Reporting Codes, your Joint Ore Reserves Committee for the Australian Stock Exchange, and then the QP statement, which is the qualified person statement, where they must declare whether they, as a qualified person, has verified the data that's disclosed, including the sampling, analytical, and test data underlying the information or options contained within the written disclosure. They must also describe how the data was verified and any limitations of the verification process, and an explanation of any failure to verify the data. So the standard of disclosure will depend on the stock exchange where the company is listed or wants to be listed. Which brings us to the fact that great data starts in the field already. So that sample acquisition techniques, field data capture. And however, it's extremely common to see companies spending millions of dollars on drilling, only to have it captured then on paper logs or Excel files, which brings me to this section of the York Code, which says measures have been taken to ensure that the data has not been corrupted by, for example, transcription or keying errors between initial collection and that data validation procedures were used. Which is a bit difficult if you think about the way that a lot of field data is captured. So by using digital tools, we can start to assist in minimizing these errors by implementing validation rules, by approval processes, and by following a chain of custody and the tracking of the samples. So looking broadly at these points, the validation of logging must start as soon as possible when we gather the data. So when we look at downhole data, there may not be any overlapping intervals. There may be no missing intervals without an explanation. So if there is broken core, there must be made a note from 3 meters to 6 meters, no core broken, or whatever the case might be. Your data must include a dip, a ASI, a easting, a northing, your RQD, your end of hole, as well as your geographical grid system must be defined. When it comes to the validation of assay data, it all starts with your core sampling procedures. So your core cutting, was it half core, was it quarter core, was it full core? The possibility of contamination within that process of your core sampling. Your sample numbers, how are they generated? Are they unique? How do you add them to the sample so that they do get to the lab and they're still readable? What kind of controls and documentation do you have in place? And your sign-offs. Then when it comes to the QA/QC program implemented, that's normally involving duplicates and standards within a known grade. This is to check your reliability of precision. So to check your precision, you will have 5 to 10% roughly of field duplicates, 3 to 5% of pulp duplicates, and your duplicates should be prepared and analyzed by your primary lab. Then bias can be identified by the inclusion of around about 3 to 5% of standards per batch. And your blank, which is a sample with a concentration of the element of interest, which is below detection limit. So currently there is no prescribed industry standard, but there is best practice within the industry. So which comes to loosely about in 20 samples, you'll have 1 blank, 1 standard or CRM certified reference material, 1 coarse duplicate, and 1 pulp duplicate, and then 5% of the pulp duplicates will be reassayed by your umpire lab. So if you want to discuss any QC further, you're welcome to contact me afterwards and we can have discussion about it, because this is stuff that I absolutely love. Then when we look at when the data gets committed to the database, there must be a field for indicating who the responsible party is for capturing the data, who committed it to the database, and if there are any changes to the data, so what changes were made and when these changes were made. So then let's look at all of this together within best practice as part of the project when looking at your data. So planning your exploration project is where it all starts, and it must align with the relevant codes going forward. So how are we going to capture it? It brings us to the geological field mapping. So if we are going to start with mapping, which systems are we using? Are we using something like ARC field maps, and will it be able to integrate all of the information that we capture within that mapping procedure further down the line within our IT infrastructure? Then it gets to the geological records. Is it downhill? Is it point samples? Are we doing diamond drilling? Are we doing RC? Is it, do we have a coral survey, the core diameter, the lithology, the structure? Everything that needs to be noted must already be included from this point. Then are we doing core recovery? Are we doing RQD? Are we doing SG? Which methods are we using? We must already start noting all of these methods from the get-go. Then once the core has come out and it's being stored, what are the core storage procedures? Are we cataloging the core? Are we storing half core? What are we doing with the core? These procedures must also be noted down. Then going to core sampling and procedures is, how are the samples handled? Are we cutting it? Once again, is there any space for contamination? Who's generating the sample numbers? Are they individual sample numbers, not replicated even between projects within the same company? What CRMs are we using? What's the documentation involved and who's signing it off? Then once it's sampled, we look at the sample dispatch, the coalition of the sample. So are we doing all of the sample at once? Are we inserting all of the blanks and the standards? How are we handling the duplicates? And what kind of controls are in place to ensure that we don't have any sample swapping? And also security to ensure the custody of these samples. Then we move into the lab space, so the analytical laboratory. So who is our main laboratory? What kind of accreditation does this lab have? What are the procedures that we are using for our assaying? What are the turnaround times and result formats for the assay certificates, which is very important? And also, do we have a referee lab? Which brings us to the insertion of our certified reference materials or our standards. Do we have a complete selection? What is the source of our CRMs? Is it accredited, such as an AMOS or an Aureus, or is it a round robin from a depositional type? Do we have the correct certification for it? does the material matrix match the depositional environment that we are checking? And what is the insertion regularity? Which brings us to our assay results and verification. So it's imperative that there is no key handling of assay data, which means that your lab should give you the assay results in an electronic format that is importable into your database. Nobody should touch that result. That result should be imported directly from an electronic file. And based on that, are we passing it or failing it based on our QC program? Are we working on 2 standard deviations or 3 standard deviations? Are we working 5 samples or 10 samples in front or following the QC program? All of this has to be noted, which brings us to our database and management software. So do we have the correct validation rules in place to make sure that we speak to the best practice, that there are no overlapping intervals, that we have end of holes, that each hole has a collar value assigned to it? And then we must look at consistently monitoring the statistics and graphs based on the results from the CRM, duplicates and blanks. This is to track the assay performance of laboratories. It's to establish if there are any biases in the data, it might be systemic or otherwise, or if there are any sample swapping or possible contamination. So I went through this rather quickly. So if you have any questions or you want to make any notes of it or ask me anything, you're welcome to it. So my last thought for this is that data is not insight. However, data that conforms to best practice will be used to inform decision-making, not only for possible investors, but for strategic business decisions. As the first step on the data chain, you are responsible for the auditability of that data that will be used to inform the decisions long after the drilling has been completed and long after you have completed your geological log. So the ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, is going to be a hugely important skill in the next decade. However, this will not mean anything if we do not have a standard that we conform to, that we can say to our qualified person that we work with, I followed these steps and you can trust the data, and the data are auditable. Thank you very much.
So yeah, let's go for it.
All right, so before we get into it, let's just think about what is reliable data. So for a geoscientist, your data underpins all the assumptions for the way the deposit will be mined. All of the assumptions are made in the mine plan. They need to be based on data that is already collected, analyzed, and is stored. So if you can't trust the accuracy of your data, you're starting at a disadvantage that's hard to overcome. Therefore, data reliability is crucial. Now, the reliability of data is, of course, driven by the decisions that you have to make based on that data, hence the theme of today. And this can mean different things for different processes, different projects, and different operations. Now, to better capture the meaning of reliable data, we will focus on some of many data reliability components, but we'll focus on the following components.
Now, there is a lot, as Andy has said, depending on what you need to do with the data, or what kind of decisions you need to make, there will be a lot of components, but we just want to highlight these 4 components today. So the first being, what type of data will be critical for my decision making? Do we need to collect everything simply because we can or we should? And I've seen this happen where you are in a mine environment and you collecting magnetic susceptibility, but really nobody does anything with that data, but you're just collecting. So it is important to start by understanding what critical data one should be collecting for which decisions that needs to be made downstream. And the second part, which also ties with what I just said now, is how much data do you need? Where do we draw the line, you know? Because yes, you need you identify critical data, but you also need to know where do you draw the line, because you can analyze for 100 elements in your ore body. Do you need analysis for 100 elements in your body, in that ore body or in your sample? So that is important to draw the line between volume or quantity and quality. And the next thing is, how do we ensure that this data is reliable then? And this is where we put controls in place, which I just said, Maria touched on that in detail. And we will just, you know, brush the surface, but it is important to have controls in place. And lastly, how do you store the data? How do you manage the data? And how do you access and interrogate the data to make sure that you can then make those decisions based on that data?
All right, so one of the things that you need to do when you're determining if your data is critical is firstly, you need to decide which data is critical for decision-making, like Dabelo has mentioned, because the type of data will tell us which equipment, processes, and solutions we will need to collect that data. And this can be based on a variety of things. For example, it can be based on certain key performance indicators that your company has, i.e. certain drilling or sampling meters need to be drilled per month or per project, or a certain sampling program needs to be followed for your specific ore body. Now, when we know which data is the right or critical data, then we can decide on the collection process. So how will you go about it? So for example, which sampling methods will you use? Which QC protocol will you undertake in your campaign? So once you know these two factors, then that informs the type of equipment that is required. So for example, that will be your sampling equipment and the different types of solutions that you can use.
Right. And then going back to quantity of data, as I said, how much data do you need and where do you draw the line? The size of the data set usually depends on the problem that you're trying to solve. But where do you draw the line in terms of optimal data? And this is something that we should think about and re-engineer our processes, because most of the processes that I've seen, they've been there and they've never been questioned since the beginning of time. You have an operation or a project that's been running for the last 30 years. And because for the last 30 years, they've done things in a certain way, it's just continuous. And the procedure that is followed was written back during, you know, Windows DOS or even before then. But the importance is we need to optimize, because quantity can never substitute for quality. So it's good to have a lot of data points so that the samples closely represent the population, but the amount of data that you have will never substitute for the quality of data. And this is where we need to draw the line. And also, whilst we are busy collecting the data and having large quantities, we must never forget the quality of data. And the quality of data, there are also some aspects that we look into. So the first thing is capturing of data. Maria did also speak about manual and digital capturing of data. Now, we also focus on validations and making sure that business and business rules and logic are adhered to at the point of capture. For instance, you don't want to end up with data where you're saying you've drilled 100 meters, but you've logged 150 meters of lithologies, or where your azimuth and your deep do not, you know, follow the business rules, where you have a deep of 100 meters, 100 degrees, for instance. So certain business rules and logic needs to be adhered to at the point of capture. This is this is the first point where you make sure that your data will be reliable, where you will trust your data. And it's very difficult to do that in an Excel spreadsheet unless you can build a lot of macros. And at the end of the day, it also confuses you, or it makes you inefficient. And the second part where we need to ensure quality of the data is during the sampling and the prep stage. And this is important because once you have your regulatory body that you're following, which were mentioned here today, you need to then have QC protocols. And yes, there isn't a generalization in the industry as to how should your QC protocol be. It will depend on the ore body that you are working on. But what is important when you collect the data is to make sure that you control for contaminations, and this is done at the sampling stage. And the next stage where we need to also ensure control is at the analytical stage. Now, at the analytical stage, we see two steps of controls. The first control is where the lab, because the laboratory needs to make sure that whatever results they send back to their clients complies and passes their own internal lab controls. So the laboratory will have their own certified reference materials that they will use throughout the process. Now, what I've seen is that most of the laboratory customers don't request this data. And it is important to understand that this results that we're getting, they did pass the lab test. So it's important to get that data and maybe some sort of standards and understand that, compare that with your internal QA/QC as well. So have double checks on the analytical stage. And on with your own CRMs, then you will make sure that you check for accuracy and precision. And I mean, highly unlikely. And yeah, where do we draw the line? Are you looking for low accuracy, high precision? Are you looking for high accuracy with low precision? Or are you looking for high accuracy and high precision? And I mean, there's all the studies that have been done in this space. But what is important is you need to understand what is critical for the decisions that you need to make, how much of the data you need to get to collect, and what attributes of the data is important for you to document, and how do you put controls in place to make sure that you can then trust the data and say this data is reliable for what you need to use it for.
All right, so we have touched on the different components of reliable data. Now, the last component has to do with managing that data. So how do you store it? How do you manage it? How do you access it? Also for analysis and interpretations. So currently, there is a consistent theme and approach to how data is managed in a lot of geosciences departments. So managing data is commonly a static linear set of relatively unconnected tasks and activities, with lots of work being done in isolation. And these tasks and activities aren't necessarily feeding the next link in the chain. So essentially, the data management looks like this ball of yarn that you see here, where things are connected, but they are mingled up. So ultimately, this approach, it does provide an answer, but only after a significant amount of effort has been invested into collating, checking, double checking, and in most instances, correcting the data. Now, does this look familiar to anyone? Sure, you are organized. Sure, we've got a database, whether, Excel is not really a database, but we put it there for the people that like the Excel. But a database is not nearly enough. You need an information management system that ensures that good data goes in and good data comes out and it's auditable.
Yes, so with that said, we just want to take a step back and look at what are the common industry challenges when it comes to to data and what makes data not to be reliable or for people to doubt the data. I mean, we've had a case study in the previous session. And when we look at the common industry challenges that leads to data reliability, to make data unreliable, we see the first thing as the data itself. You find that data is stored in multiple databases with lack of consistency in terms of business rules and processes. And this leads to data that is unverified and unvalidated in the database. You also have multiple versions of a database and some errors in your reporting systems. And all of this, also including multiple data formats, makes it difficult for data managers to actually mine through what is good and come up with something that they can use to make decisions. So and overall, we don't have a single source of truth. The second thing is that we see when you have all the systems that Andy just showed us, there's always a person or an individual who knows how to build all these macros, and they will build all these macros that do validation and all of that. But the problem is that person's IP, and should they leave the project or the business, nobody else knows how to handle that. Or should the processes change because we live in a dynamic environment, nobody knows, there's no data champion or internal capabilities to support the data management solution. Thirdly, we also see that there's poor processes and poor documentation. And this comes from a poor process design where you didn't have a bigger picture when you started. We just build this data solution like Lego. Every piece that you need, you just add it in there. And at the end, you end up with this massive, complex, bespoke solution that nobody can support and is not well documented for new people that join the organization and that needs to work with it. And lastly, we also look at the cost. So at the end of the day, you end up with direct and some indirect data management cost because of the inefficiencies that you have in the workflow. So with this common industry challenges in mind, we'll move to the next slide.
All right, so you see very commonly, you do know that the data exists and you can find it eventually. But being spread over different networks and shared drives and folders and spreadsheets, or if you're more sophisticated, some SQL database, it provides little context to what you're looking at. So there are some questions that you have to ask yourself. Can you readily understand the data that you found? Why does this data that you found exist? And where did it come from? So who has had a part in to play in collating it? And has anyone modified it? Or are the formulas in the spreadsheet, if you're looking at a spreadsheet, are the formulas okay? I bet they're not. It's likely that they're referencing the wrong cells. And also, how can you trust this data? And if it's hard to understand what I'm looking at, and I can't trust the veracity of the data, how confident are you in using it to build your resource and geological models? How confident are you in using that data to do your reporting, share that data with shareholders, or make production decisions on it? And most importantly, how confident are you to let an auditor loose on that data? So if you go through this list, and that's on the screen here, and you kind of basically moving down the scale of confidence. And if your confidence is eroding, that level of risk just begins to increase. So if the data you need exists, and if you found the data that you need, if you don't understand the data that you found, and if you don't trust the data that you found, and finally, if you can use the data that you found, then most likely someone did an average job of data management.
And with that said, and most people will say, so what? yes, the process might be complicated, but we understand it. Yes, our data management might be questionable, and it might be a black box that nobody can really explain. So what? Because we can meet all our reporting requirements and we can answer questions when asked. But what we've seen is that there is an increase in risks, which is unnecessary, because yes, you can eventually have good reporting, but there are delays in terms of regulatory and operational reports. You find your resource people having to spend time, hours and hours collating and fixing errors, which delays your production and consumes valuable time, which people could be using for other things than just fixing data. And also, you might end up having to incur costs because some of the data you might not find, and you end up having to go back and resampling or relogging or even redrilling, which now comes with at a cost to the business. You end up missing deadlines. You might not have diligence in your reports, and this might end up, resulting in fines or even litigation. So as you can see, poor data management can have major impact on operational efficiencies and eventually to your license to operate. And that's why we're having this discussion today.
All right, and just to repeat on what we've been saying, basically, a database is not nearly enough. You need an information management system that ensures good data is in and out, and it is auditable, goes in and goes out, and it is auditable. Now, this is where the geoscientific information management, or we'll just call it GIM, plays an important role. It is defined as the discipline that concerns with the management of geoscientific data. So you know that the risks are there and they are real, but the beauty is that they are solvable and the outcomes are so worth it. Now, in solving your problems, you need to understand a couple of things. So the problems are solvable through understanding the data. Now, by data, we are talking about the observable, qualitative, and quantitative geoscientific data, which is a vital asset in all mining organizations. So you definitely can't talk about an ore body if you don't have the information to back it up, right? So the problems are also solvable through understanding the activities. So the activities are the actual tasks that are performed by an organization to collect that data, such as the drilling or sampling programs. And then you also need to understand the practices. So practices are the methods that are put in place to confidently achieve a desired and acceptable outcome in a consistent way. Practices such as those around data management. So for managing geoscientific information, this includes QA/QC protocols, which ensure that there is high quality data, sampling techniques, even your dispatching, how you are handling your samples and what kind of controls are in place, and of course, your logging methods. Now, the previous slide that Gabriel was touching on, it outlined how it is important to have reliable and quality geoscientific data. We need to mitigate the risks associated with poor data, and the outcome of getting this framework right is so worth it. Now, I'll let Gabriel elaborate more on this GIM framework.
Right. So Andy did say that the problems are solvable. And today we'd like to introduce you to the Geoscientific Information Management Framework. Now, when we look at the framework, it consistently has 3 pillars, which is people, process, and technology. And this is so valuable, and it works for both simple and complex environments. So when we talk about people, we're looking at the human dimension, the roles and behaviors that should be aligned to the goal of the organization. The process is how are we going to achieve this result and make it repeatable so that it doesn't depend on individual, but is a process that is just running on its own. And thirdly, technology, which is just the tool that enables people to execute the process. But as effective as these 3 pillars are, we currently seeing that there's now a new fourth pillar, which is leadership. And this is because the fourth aspect, which is leadership, provides support and priority that is necessary to develop information management capabilities and maturity. And when we look at these three pillars, unless they are supported and guided by the organizational leadership, they really mean nothing. So going a little bit deeper into leadership, without effective leadership, any process that we put in place will not stand the test of time. So we need effective leadership to make sure that processes that we put in place are there and they are followed. But what are the things that we should be thinking about when we talk about leadership? So we need to think about how we communicate the purpose and the value of geoscience data. How do we get widespread engagement, adoption of this management system? And how do we measure success on the system? And also, who's going to champion it? So I've got three pillars there. So vision plus responsibility plus priority gives the organization purpose. With vision, we're talking about a vision for the destination that will be developed. The capabilities to achieve the vision must be developed. So, and once they are developed, they need to be implemented throughout the organization. So we need to think at a strategic level, a framework that will say this is the vision for geoscientific data management. And the second pillar there is responsibility. People need to be appointed to a task in order to lead geoscientific information management for the organization and for governance. So you need people who are appointed and given a mandate. And lastly, we need to prioritize the importance of geoscientific data as a critical business aspect. And I would, we all know how much investments companies put into collecting the data, but we also know what priority is being given to this data. So we need leadership that can explain the importance of this data and present it to the business as critical business asset, so that you're not always questioned when you need to spend money on taking care of this data, making sure that it will be reliable for purposes that you need to use it for. So leadership is at the center of these pillars. Then the next one is people. Now, with people, we all know that people are the most important aspect of any organization, because the ultimate outcome of the people component is that you need skilled people who are aligned with the business or the goals of the organization. And the three components that we have under people are the role. I've said this before, people must know their role within the system and understand their responsibilities. Secondly is building a culture. So there should be a culture of data management. There should be accountability where everybody or every person that touches data must be held accountable for their action. And it should be designed in such a way that the integrity of the data is maintained at all costs. And lastly, we need to skill the people. So when all these roles are well defined, you'll have a mature data management culture. You'll have appropriate skilled people who will lead these engagements and who will take pride and ownership in the data. And lastly, we will then talk about process. Now, when it comes to process, this is important to mention that technology only facilitate a process. So first we need a process, and the process must be matured. And a process doesn't reach maturity simply because of how long it has been in place. It reaches maturity because it serves the purpose. Because at the end of the day, we have this data it needs to be reliable. We need to be able to work with this data, and we need to trust decisions that are made from this data on a daily basis with all our reporting for the continuity of our solution or our business. So if we look at the three components that I've highlighted here under process, the first thing is the single source of truth. You cannot have a process that says a certain data that encompasses siloing of data. You can't have siloed data and documenting that. So the first thing is that you need to have a single source of truth where everybody knows where to go to get certain data, because we know the process that got the data into that source had validation at the point of capture. It was following business and business rules and some logic that has been put in place. So the first thing is that you need to have a trusted source of your data. Then the second thing we look at design. So our process, the processes that we design, they need to result in quality. They must be auditable. They must increase efficiency and be able to adapt and change with the dynamic requirements of the business. So they shouldn't be so rigid that when the business changes, our design doesn't go with a change or the requirements of the business. And everybody must understand the design of this solution. And lastly, there must be skilled people who are responsible and own these processes. And one thing that we also fail to look at is the importance of a succession plan. So when all of these components are well documented and accepted, then you end up with a mature process that ultimately you can trust the data and everybody understands. Now, the third component is technology. As I said, technology is not a silver bullet. It doesn't mean because you have the best technology in the world, then everything is sorted. It only completes the picture and it balances the relationship between skilled people and your matured processes. So we must always keep in mind that we need skilled people who understand the organizational goals and have been given the tools, and we have processes that facilitate how those people go about to reach those goals, and technology just comes to enable it. Now, there are also components that we look at when we talk about technology, and the first thing is the architecture of the technology. We live in a world where nobody does it all. So we understand that we live in a world where we have certain technologies that are serving a niche part of the entire mining value chain. And we might need a number of technologies that we put together in a system in order to achieve the goal that we need to achieve. So you need a technology that allows or can work with other related systems. And that should be clear. It shouldn't be even debatable whether it can work with this or that. You need a solution that can work with other providers so that you have a connected or an integrated architecture. And the second thing is that the technology must be able to scale. As the business grows or shrinks, the technology needs to have the capability to also grow and shrink with the business. And lastly, it must also be accessible. So people need to be able to work on this technology wherever they are and however they want. And you need a solution or a technology which people want to use because they understand the importance of this component and they understand the efficiencies that it brings. And when you have all of these components together, then you are ready to deliver a technology that is an enabler to your skilled people and your robust and matured processes. And this now completes the GYM framework where you talk about people that are skilled, technology that enables processes and a matured process with leadership ahead, making sure that everybody has the skills that they need. And when you have that, then you will complete the picture. And what you see now on the screen as a picture of how do we then complete all of this. So at the bottom, you will then have a database that caters for different parts of the journey. So from your drill holes, your surveys, your logging, your blast holes, your samples, whatever you are doing, your quality control as well as reporting, you have all of this in a single source of truth where everything sets in. And that's what Gym Suite provides for you. And then on top there, you have a number of players. So remember, I spoke about not having a siloed process where everything is in different places. Now that you have a single source of truth, you need to be able to have different roles within the mining value chain, being able to access that environment. So you'll have geologists who are dealing with your exploration and production or grade control, drilling and sampling. That information will then be used by resource geologists to build those models. You'll have production geologists building their production models or estimations for day-to-day production work. You'll have geotech building their models. You'll have geometallurgy doing the same. And all of this then feeds into the plan where it goes now to mine planning software. Same data, everybody's using the same data, the concept of a single source of truth. You can now determine your resource and your reserve. You can now work on your life of mine reporting, and you can also start using the same data now to now determine your long-term, your medium-term, and your short-term planning. And this also links back to reconciliation and depletion of your resource as your operation complete. And all of this happening in one environment. I liked what Maria said when she said that there shouldn't be, the laboratory shouldn't be giving you data that you are fiddling with. It should be data that you can directly import into your database so that you can use it downstream. And that also helps with the integrity of your solution. So in a nutshell, to make sure that you have reliable data that that you can use to make business decisions downstream, you need to have a process that is matured, personnel that are skilled, that understand what the organizational goals are, and a technology that allows you to have a single source of truth where everybody connects all their tools, the tools that they need to work with into that technology. And it makes this critical business asset that we call geological data very important, that everybody uses it, everybody wants to use it. And eventually you end up with a solution that integrates the entire organization, and it makes processes very efficient. And not forgetting the leadership that will understand the critical data that is being collected, as well as the quality and the quantity that is being collected, making sure that they lead this initiative going forward. And if you have all of that, there's no doubt that you will be able to trust the data that you'll be making decisions on. You'll have a higher level of confidence in your reports that you produce simply by taking care of the basic fundamentals.
Mhm. All right, so in conclusion, as Deborah has mentioned, what the ultimate goal of establishing this balance between people, process, technology, and leadership is when you're looking through the lens of reliable data, it is that a mature GIM framework de-risks your scientific workflows. It increases the data integrity and thus your trust in the data. And when you trust the data, then you know how it will impact your models, you know how it will impact your mine planning, you know how it will impact your reporting, and most importantly, you know how it will enable you to make critical decisions for the organization. So you arrive at a point where you can go down this list with a peace of mind, because if the data you need exists, and if you found the data that you need, and if you understand the data that you found, and now if you can trust the data that you understand, you can use the data that you trust. And you know, at the end of the day, someone has done a great job of data management. And with that, that's the end of our presentation. Thank you guys for your time.
All right, so today I'll just be speaking about data analysis and visualization with Python programming. I know it's not necessarily sampling or protocols or data management per se. However, I think it does have a role in data management. It does have a role to play in data management. Python is quite versatile, so I hope you guys get something out of it, and I really hope to inspire some people today to maybe even use Python down the line in some of their workflows. So thank you everyone for joining. It really is a great privilege and honor to be able to present this talk. So first, I just want to lay out what I'm going to be talking about in our presentation today. Firstly, I just want to go through an introduction, a brief introduction into Python programming and why you would want to consider it to adding it to your tool belt as a geoscientist. And then next, I just want to get my pen up, sorry. Next, go some Python libraries, which have been built in Python by some very clever people to help us work with data and visualize it in a meaningful way. And then after that, we can go through some of the reasons why Python is so powerful and how it achieves power through some of its core functionality and syntax. And then next, we can dive into the overview of how one might use all of this to perform some data analysis and visualize your data to help solve your problems and facing in the real world or in your projects you're currently doing. And then we'll go through how to get your data into that workable format and some of the standard tools that you'd use in Python to allow you to explore that data in a rapid and consistent manner. And then lastly, we'll look into some snippets of codes and methods that you'll be using to use in your data analysis campaign, and then what you'd be able to expect while doing so. And then finally, we can wrap up with some use cases that I've applied and maybe you'd like to apply in some real world mining and geology industry use cases. First off, what is Python? Python in general is a interpreted, object-oriented, high-level programming language with dynamic semantics. And its purpose is to be able to provide a good application development, which is easy to understand and align to our everyday language. And Python is relatively simple to read and write. And also, most importantly, it is open source, freely available to anyone who is interested in using it and wants to know how to use it. So why use Python? Python offers us a way to really reliably streamline or automate some of our daily processes, which in times can be very time consuming and tedious. Python can also even replace some processes that are kind of impossible to achieve without some fancy or expensive software, which you may not be able to afford in your budget, such as maybe some of the functionality I'm going to show you later on. And that would be how we can replicate some of the functionalities of a software called JMP, which is marketed as a statistical and analytical software, which is mainly used to perform QA/QC on assay data from the lab. And we all know that time is money in business, and that's no different for the mining and geology industry. So finding some ways to automate tasks that would have taken hours or even weeks to complete may be achieved in a matter of seconds if we know exactly how we want to process that data, put it through Python programming. And here you can just see a little silly program that tells you time is money, and you'll see that syntax is not necessarily so complicated, and it's much like some of the high school mathematics we all went through at school. So first off, let's take a look at some of those important libraries that have been developed for Python, which makes that whole automation and data analysis business walk in the park. But firstly, Python libraries are essentially a background code that is running in the background, and it's being developed by these insanely clever people that makes our processes quite fast and user-friendly. And first of these libraries, which is really important in any sort of data analysis tool workflow, is NumPy. NumPy enables us to generate fast numerical computing, from mathematical functions to random number generators, linear algebra, and some data transforms. And secondly, built on top of NumPy is a platform called Pandas, or library called Pandas, which enables our users to manipulate data structures and perform high-level operations such as quick mathematics and or statistics. And Pandas, in my opinion, is probably the most versatile and useful tool when dealing with any data set analytics and filtering. And essentially, this is like your Excel, but in the background. So 3 lines of code rather than visualizing a table format, which you're very familiar with in Excel. And then next to Pandas is GeoPandas, which is used to manipulate geographical data such as geometry and polygons in real space. So a lot of geologists and geoscientists, or even mining industry guys, will be using data that is measured out in the real world, and we want to analyze specific aspects of those real world objects. And GeoPandas helps us visualize and facilitate that process. Next, we have a library called Matplotlib, which is a powerful package allowing us to create amazing customized graphics based on our data so that we can show our results of any data analysis in a meaningful way to whoever needs to see it, mainly in our reports and showing our boss what we've done. And here's just a snippet example of how you can use Matplotlib to visualize the predicted outputs as well as the performance of a machine learning algorithm which applied to some rhodium regression. And on the bottom left here, you see an example of the predicted values versus the output values, or the actual values, sorry. And on the right, you can see the performance metrics or the error metrics of well, did the predicted versus the actuals really do. And that's in a frequency histogram format. Moving on to other plotting libraries, which are a little bit complicated, but have a lot more power behind them, and that is Plotly and Seaborn. Now, Plotly is a library that provides an interactive data visualization tool for creating charts and graphs and maps, etc. And this is a way of you being able to actually zoom in, click on data points, and distribute this and embed this into some kind of web application or a dashboard where now you get live updated data and you can manipulate that how you want to. And then Seaborn, which is built on top of Matplotlib, provides a high-level interface, so it creates nice, attractive maps and informative statistical graphs. And also it offers a variety of plot types, including scatters and line plots, all different types of plots you can think about, really, but is less intensive than Matplotlib and achieves the looking plots with less effort in the coding realm. So these libraries are really great. However, I think the most fundamental aspects of our coding in Python comes from its build structures to handle logical problems. So the first of which of these structures in Python is called Boolean operations. And I'm sure if you've ever worked on some data in Excel or any other data, that you've come across filtering of data in a sort of more visual format. And maybe you haven't seen it in such a raw format as the words itself, but the principle behind that filtering is based on Boolean operations. And these are simple words such as and, or, not, if, and these are used conjunctions to combine or exclude keywords or mathematical truths. And that results in a more focused set and productive set of results. And as you can see, you can have two data sets or one data set that's combined, and we can grab or slice data sets into smaller chunks, which are tailored to exactly what you're trying to perform an analysis on. And these operations, these Boolean operations, are crucial to extract our necessary information from the data sets. And what's really great about Python structure that it really does allow you to do this with very little effort and extreme speed. Next, in terms of the core Python functionalities, just probably the most fundamental is the for loop. Now, the for loop, as implied in this diagram, is achieved by running through a set of conditions to be met. And then you apply a function inside of that condition over and over. And this will be done repeatedly until that condition is met. So you can see we initialize, we have a condition, and then we have a function that is applied over that condition multiple times. Now, say you have an example where you have a massive, large data set, millions of rows, and you want to calculate something specific out of that data set, but you need to calculate over specific individual classes separately. So we can use this for loop to go through all those unique classes in a data set and then calculate them over and over using this one simple function that lies within the for loop. As you can imagine, this is an incredibly powerful way of processing data, and it really does truly outpace any way of manually doing these calculations in an Excel spreadsheet, and by a long shot. So that's the core functionality. But before any data analysis can begin, and I'm pretty sure as you've heard previous talks and some further talks that will be after me, that cleaning and wrangling data is a really important process before any data analysis. So you need a meticulous approach to understanding and cleaning your data before doing any data analysis. Most data sets inherited historically or currently being made without any sort of data geological framework or data framework are full of blank cells, typing errors, or data type mixing. And dealing with this messy data is the first step to any successful data analysis campaign. So luckily, the previously mentioned Pandas library has many built-in methods to help you keep a well laid out and clean data sets. Some of these maybe include dropping all those null values in a specific column or throughout the entire set. You want to search specific unique data entries within a column, as you may not know what's in this column or data set, as it can be so large, we don't know what's in it. Grouping our objects into specific classes so that we can hone in on specific groups of information. We want to transform our data into a different format, or just remove the unnecessary information, or do some high-level calculations. If you want to calculate some block model metrics, calculating per block or cell, you can transform your block model into sort of a resource evaluation model. And there's many more different methods that Pandas can be used for to get a well-rounded data set. So this is an example of some of the things that you might do in a data wrangling data workflow in Pandas. And first, you would need to read in any data that you currently have, or the set that you have in CSV format, Excel format. There's a variety of different formats you can be used here. We need to drop all those missing values. Maybe there's duplicate value we don't need. What I'm trying to demonstrate here is that we can achieve a large amount of processing and transformation in our data sets with very little effort in Python because of these built-in libraries. Say we have a column in our data set that has a date, but the software that we are trying to stick it into afterwards to do more processing uses a specific date time format. Obviously, Excel may be able to do this as well, but we can do this in Python as well. We need to create a new column from two numerical fields by adding them. Very simple. We can group our variables together and then calculate the mean. Resetting the index so we can keep track of where the values occur within our data set. And obviously, we want that clean data set to be extracted, and we can create a CSV of clean data. So what does clean data look like after all of this processing and wrangling? Well, hopefully something like this example. All the fields contain the same data formats. There are no missing values, etc. So this is really what you should strive for your data to look like after all that wrangling, which, to be honest, in light of data analysis and visualization using any platform, especially Python, and that's going to be the most time spent, is understanding and trying to get your data in format that can be analyzed relatively quickly. And like I say, the latter is relatively easy and simple after we have really clean data sets. So let's move on to the fun part of this presentation, which is the actual analytics of it. So what is data analysis? Data analysis is the process of evaluating, transforming, and or modeling your data in order to extract insights and draw meaningful conclusions so you can make decisions. And this can involve various techniques such as descriptive stats or exploratory data analysis, algorithm transformations, machine learning, or all of the above in one project. So Python can offer you a series of amazing tools that are freely available and easy to use, and that allows you to gain near instant access to these valuable trends in your data analysis and get the relationships within that clean data set. Now, I've just included a few here that you may come across when embarking on this type of workflow using Python. The list can be infinitely larger than this, but for the sake of keeping your interest up for the rest of the talk and not scaring you away by delving into some convoluted and very complicated Python methods, should be good enough for the purpose of this course. So we'll go through these 5 different methods and how they can help you in your data analysis or exploratory data analysis in Python. First off is pandas profiling. And second is describing data statistically using Seaborn to show relationships in pair plots, plotting that information in 3 dimensions and visualizing it and interacting with Plotly, and then extracting unique data and using filtering using pandas. So let's go through those individually. First off is pandas profiling. And pandas profiling is a library that allows you to quickly generate a comprehensive report on a data set. And that includes the statistics on each variable, the correlations between the variables, visualizations of those variables, and what is the data distribution. This can especially be helpful for any geoscientist or industry professional who's with large and complex data sets that they've never seen before, or want to understand a little bit more about the way they can improve on the type of data they've collected. So for example, if you have a data set that maybe contains measurements of rock properties like porosity, permeability, lithologies, pandas profiles can generate that report that can summarize all your univariate statistics like the range, mean, and standard deviation, each of those variables, as well as some histograms, scatter plots that visualize those relationships between the variables. And this can really help you identify patterns or anomalies in the data to make informed decisions about how you want to analyze going further or how you want to model your data. So in addition to providing basic statistics and visualizations, pandas profiles also offers a little bit more advanced features, cross tabulations and correlation matrices. And that's especially helpful when you're trying to understand how different variables interact with each other. and how they might influence the geological processes or phenomena that you're studying. So I think it's a powerful tool for people who really need to quickly and thoroughly explore a complex data set. And in this example over here, I've shown you this is what you can expect from a Pandas profile report. And you can, within 3 lines of code, be able to generate this report on your data set. And you can also save these reports as an HTML file for constant and easy rinse while you're exploring your data further in another software. So this is savable and you can always refer back to it and interact with it how you need to. The other method was describing your data. The describe method is a built-in function in Pandas that generates these basic statistics. Wording is not my strong point right now. Basic stats on a data frame or a series object. So it provides a quick and easy way to get a sense of the distribution of your data and the central tendencies of a specific data set. So here we're looking at a data set with 3E values and what the distribution of that 3E is. Moving on, we can use Seaborn, as mentioned, to generate a pair plot, and that allows you to have rapid visualization of your data set correlations. So with a data set, an assay data set like we are using in this example, we can see how each analyte or each element is correlated with each other, and we can see that visually quite quickly, which are the elements that are going to be most influenced by each other and which are not. And how do I make a decision on that? For example, if copper is associated or has more of a linear trend and is highly correlated to another element, and if we're targeting that other element, maybe we can look, while looking at the core, we can be looking for chalcopyrite to know with a bit more certainty or a little bit more confidence that I may have some higher grade in this other element that I'm looking for. And here in the bottom right, you can see an example. It's just 1 line of code, and you can generate this pair plot, or lines of code, may I say. And then Plotly. Plotly is like I've described, a Python library that allows you to have interactive data visualization. One of its most powerful features, I think, if you are a geochemist or if you're studying assay data and need to understand what the relationship in your variables are, you can create these multivariable 3-dimensional diagrams and plots, and you can interact with them. So I just want to play a little video here. I hope it plays. You can see a little demonstration of how you can interact with the data three dimensions. So in this plot, you're actually seeing more than 3 variables, other than palladium gold. You see there, you can actually see the ratios of color on the right-hand side between calcium, magnesium, as well as size of the bubbles will be describing a different analyte that may have a correlation. So that's relatively great in terms of data exploration and seeing these variables correlate with each other, not just in the 2-dimensional space. And lastly, this is something that I use frequently, and I think it's important to touch on. But just 1 line of code, say we have a data set that is really large and we need to know exactly what type of categorical data has been placed in this data set. And usually you would have a good knowledge of what type of data you already have in that. But if you're not familiar, this is a great way of finding that information. Here you can see we've extracted all the unique values that are within a specific column for stratigraphy. And this, when coupled with the for loop, can be powerful, as now we can group by these specific stratigraphic codes, and we can loop over these stratigraphic codes to perform an analysis on any other variable that is associated with our data set for these stratigraphic units. If I wanted to calculate composite grade values, or if I wanted to find out what lithologies are the most common within each of these strat units, I can use for loop and write a code inside of that for loop that looks at every one of these individual strat units. So use cases, like I mentioned before, we can try and replicate the use case, replicate the software capabilities of JMP to do QA/QC on some assay data. And now this is just a snippet of a code that does that. But over here, we are creating a function which reads in specific information like what type of AMOS code are you using, or AMOS sample, what type of analyte you want to figure out the accuracy on, which project you may be working on. We can figure out how well we did in terms of our quality control, or how well the lab did by placing specific analytes or data entries that get back from the lab into a specific category, passed, failed, or warning. And this is what the output of that would look like. In a control graph, we can see our second standard deviations, third standard deviations, the certificate values, and we can see how well we did perform, provide percentage of failures versus passing. And then on the here, we can see a vision plot where we now can see just how much of the data is close to each other. Or this is a half absolute relative density plot. And here you can see percentile rank on the x-axis. So how much of the data currently falls within. So over here, you can see just how well your precision, or how precise your data is in terms of your duplicates and your primaries. And then next, some more examples of use case of Python analysis and visualization is RQD versus structure length here on the left-hand side. Here we can see how structure length may be correlated to the material recovery, and that may be some useful information that you want to have prior to designing some kind of geotechnical drilling program when you're doing either a shaft, sinking a shaft, or designing some slopes for an open pit. So this information can come from your logging, and the database can quickly plot these relationships. And then on the right-hand side, another use case, maybe from all your logging, we can have a histogram of all the different types of alterations that were logged in this program. And when informing our metallurgists down the line, when we want to process and extract metals from the rocks that we are studying, or we're trying to mine, we can inform them on what types of alteration they most likely may be encountering. So that may be useful down the line for metallurgical processes and for understanding processes as well if you are studying alteration. And lastly, another use case, before I jump into a live demonstration, I don't know if we've got time for a live demonstration, but I'll try to zoom through this. A much more complicated data visualization method in Python, which uses a library called PyGSLib. You can actually construct drill holes in three-dimensional space, survey them, and composite assay data so that you can interact with this in 3 dimensions. I unfortunately don't have a video showing you interacting with this, but you can imagine you can maneuver in the 3-dimensional space as you would in any other 3-dimensional software. And that just shows you how wide the application of data analysis can be with Python itself, depending on your level of skill and obviously want to do so. So I don't know if I can jump into a quick live demonstration of this data analysis with Python, just going through some of those things and showing you how easy some of those methods are to do. So the first thing we have to do in any Python project is import all those libraries that will provide that core functionality we want to achieve. So here you see NumPy, Pandas, Matplotlib, and Seaborn as the libraries I just want to demonstrate in today's example. And we'll load these libraries, and you'll see just how quickly all these things happen. We want to read in our data set using Pandas data frame method as a CSV. And first we want to see what our data looks like using the head method of data of that data frame. And once we do that, we can see, all right, this is what our data frame looks like, the first 5 rows at least. And it looks like we have drill hole ID, sample ID, the intervals where the samples were taken, and obviously the assay results that were received back from the lab. Looks like we have maybe some missing values in this database or this data set, which we'll come to in a later part of this demonstration. So let's take and make a summary of these basic univariate statistics for each of these elements using that describe method we've talked about. So we want to list all the analytes that we have in our data set, and we want to describe them and get the statistics. And here we can see we have a almost immediate output of the distribution of our data and their central tendencies, where the mean lies, where the maximum, minimum values are, what type of standard deviation are you thinking about in terms of this data, how many records you have per analyte as well in your data set. You can see rhodium here may be suffering from a large amount of missing the information, as well as platinum, palladium, gold versus copper. So let's take a look at how these elements in our data set interact with each other by plotting that seaborne pair plot. And over here again, we're just going to be calling one line and calling those elements again, and we'll be able to generate a plot. It may take a little bit of time, as there's quite a bit of data to plot onto these pair plot graphs, but it shouldn't take much time. Just seconds, really. So over here now we've generated a quick scatter plot and correlation plot using this pair plot method in Seaborn. Now we can see just how related some of these elements are to each other. And you can see here each column refers to a specific analyte and each row refers to a specific analyte. Here we can see whether or not certain elements are more related to each other or have a linear relationship with each other or have no relationship at all. So that's quite useful and handy when you haven't seen a data set before or you just want to get more insights out of it. So these methods above are really a great way of gaining some momentum in understanding a data set. And that's relatively quickly. We've only spent about a few seconds or maybe a few minutes doing so. But I think this next method, the pandas profiling method, is the most comprehensive and user-friendly. So we want to import that library, which is the pandas profile report. And we then want to generate that profile report in this line of code using our assay data set. And then afterwards, we want to generate and see what it looks like. So again, this will be processing it and creating a interactive window that you can see the variables and how they interact with each other, maybe where the missing data is as well. But I'll take you through that. All right, so it doesn't take too long. And we have this full-on report about our data sets. So you can see we have an overview, variables and interactions, what the correlations are, missing values, and some sample information. So our overview is quite nice. You can see just how many observations we have, how many variables we have in our data set. And this is something quite interesting for this data set that I mentioned before. We may be suffering from missing values. So there's a lot of misses, and that actually equates to 22% of this data set. And then we can migrate to our variables and we can see what each variable is individually. And over here, we can see that we have maybe 204 drill holes in this base that we're going to be analyzing. We can select the different analytes over here and see what it looks like as well. So we can see just the missing values we have. Maybe we have 33% missing the palladium. We can see, again, our descriptive statistics provided to us over here as well. So this is really great interactive tool just to get more information about your data set really quickly. We can also see the interactions between these analytes or these different columns within our data. So platinum and palladium, and see how they work. Unfortunately, I'm not a fan of this, and this is why I showed you the SNS or the seaborne pair plot, as the axes are quite fixed in this report, and there's no way to change this unless you go through a little bit more complicated, which I think is not really the reason why I'm showing you this. But you can maybe in a different data set see better correlations in this sort of format. And we can see our correlations, and we have this correlation matrix. And obviously the correlation over here on the right-hand side, the higher the value is in terms of this heat color, the more correlated the values are to each other. We can see, yes, there may be quite a bit of correlation between rhodium and nickel, and then it gets less so. Now, in terms of the missing values, I think this is mainly part of what I want to show in the demonstration of visualizing this data and maybe doing some core functionality of Python and demonstrating that to you. It looks like there's quite a bit of missing data, and we can visualize this in a matrix net where we can now see the entire data set laid out in one area, in one picture frame. And here you can see where the missing values are in your data sets. We don't really have any missing data for these 4 rows, but then we start to have missing data in the analytes. And obviously rhodium, gold, platinum, palladium have quite a bit of missing data. And that may be something we want to investigate in a historic database, or something in our current database where we need to go and fill in the gaps, or we need to go and try and figure out where we can improve on our current data sets or take new samples. All right, so let's create, this is what I want to show you. And I want to create a series of grade profiles for each of these drill holes. We have 203 of them, if you remember, in our data set. And based on our visual inspection in the Pandas profile report, we need to be able to see where in each drill hole there's a missing sample or result for an analyte. So we can go through that process just quickly. So in order for us to look at each individual drill hole, we need to create a list of unique drill hole IDs. So we're going to say unique function, which we've used, or I've shown you in the presentation. We're going to create a list of all those unique drill holes. And this is where that core functionality of the for loop comes into play. Now the for loop will loop through this list of drill holes and apply the function that I have below the for loop. And this function essentially is going to be plotting the information in a grade profile, like mentioned before. So first we need to read the information into a data frame from our CSV, and then we would need to, now I want to actually use E3 as one of my plotting tools. I don't want to plot one of these individuals. I want to actually create a new column. So we'll add platinum, palladium, and gold together, create a new column called E3. And now this is where we can have a conditional statement in the Boolean operators. And that means I can now slice my original data set by the drill hole where it is equal to one of these in my list. And then it will perform everything and go back and become the new drill hole. And so this way I can look at each individual hole at a time and then plot the graph of it. And this next one, this is a method that I want to now identify all of the missing values in my data set and replace them with a negative value. And that is for visualization purposes. So where I had a missing value for a specific analyte, I now have a negative 0.05 value, which I can then see in a graph format further down the line. And then further down the line, I want to split this data into the data that I currently have and the data that I don't have. And this, well, now this is again Boolean operations. This operator is not equal to this value, which is inherently a missing value. And then the missing values is equal to this value that I've assigned to all the missing values. And then we'll plot these on one on top of each other, the have and missing values. to generate a series of bar graphs. And then at the end over here, we will just save these into the same file directory that we have our CSV or assay data sets. And we will call them by a bar, the name of the drill hole, and the profile. So if we run this, it may take a little while as it's now looping through the entire data set to generate these grade profiles per drill hole. So it may take a little while as it's trying to do a lot of it once. But what you'll see is that if we go into the directory in which we were working with this assay data set, I'm now producing a series of grade profiles per drill hole and saving them as an image. And it's looping through the entire data set now and creating grade profiles. We can open one of those up to see an example of what that looks like. So here we can see the name of the drill hole. We're looking at 3E and we're looking at the depth. So all of the information that is on the negative side over here, which is at 0.015, I can see where we have missing information assay wise. And maybe that has a huge implication for how I go about naming a stratigraphic area or make a decision about where we need to assay next or where my budget needs to go to in terms of planning the forward moving parts of this project. So that's about it for my presentation and demonstration. I hope you enjoyed. If you got any questions, we can take them now. Doesn't look like we have any questions.
I see Marsha has her hand up, Mike.
Oh, sorry. I'm not looking at the, yeah. Hi there, Marsha.
Right. Hello. It's not a question. No, I just want to congratulate you. You know,
Oh,
Michael,
appreciate
you know,
that.
I must say, you make me want to go back to being a programmer, but I can't, you know. No, I've spent my life. But you see, the advantage of something like this, or of Python, and rapid application development languages, but platforms. But I mean, Python is now well developed and quite mature, and I think it's a good choice. I also want to say I think it's a much better choice than putting geologists onto SQL, structured query language, because SQL, what people call scripts, it's actually programming code, but you need to understand database theory. And you also need to understand the meaning of the data itself. So
For sure.
this to me is a much better approach because, as you say, it is simpler. It's those basic programming structures that have been there ever since, you know, I was born on a mainframe. People are shocked when they hear that, but it's very true. They've been there ever since then. That means they've stood the test of time and they work, and it's not going to change, by the way. There is nothing new under the sun. People just build on other stuff, you know, and it gets
Existing structures.
more high level. Exactly. And one of the principles of software engineering is that you must build on what works. So these guys have built on what works, built on what works, built on what works. So I think, you know, this is great because you are the super user, you're the geologist that understands his data. And now you can do your what ifs and things and in a very fast way. Well, I mean, don't be too fast, but I mean, you can, well, you can see a thing graphically fast, which means that you can see if you've made a mistake as well, you know.
For sure.
SQL query language, you can, it's very easy to make a result set that is completely wrong and people won't even know. You know, that's what I know from my perspective, you know.
If I may comment, Marsha, I think SQL definitely has its place, and I think it will always have its place in terms of database management, in terms of structuring data and creating the relationships that are required for a relational database to exist. And that also just helps data stay clean and stay in the right format so that maybe you don't need to have a exercise like I've demonstrated in terms of data wrangling using Python. But I think SQL definitely has its place in terms of the database structure and keeping data in line with the set sort of standards that you put in place previously.
No, you're
But
right.
in terms of Python, I think you have much more of a versatile tool to work with the data you extract from your databases.
Exactly.
And it also helps in terms of managing your data, as well as may be able to pick up some things that you didn't pick up while using your database using SQL.
Yeah, sure. So I hope that you will continue to teach this and encourage people. And yeah,
I hope it has
see
inspired
what we
people
can
to
do. Yeah.
to carry on and maybe learn a little bit of Python themselves. I hope so.
Yeah, great.
Thank you.
So yeah, my name's Mark Butcher. I'm one of the data management specialists for Sequent here in the EMEA region, based out of the UK. What I want to talk to you about today is what we've learned from the customers that we've been speaking to over the last few years, and what we call our drill hole to decision workflow. So we're looking to streamline this for our customers, and how our cloud solutions from our product portfolio can help enable that. What we've seen is the inefficiencies in the data collection and data management process cascade through to become much larger inefficiencies in project modeling and management further through the workflow. So that cascade, that effect, that cumulative effect of what was a small issue at the outset becomes a really significant problem for the resource estimation team down the line, for example. Not just an issue for our mining customers, but across all of the markets, and a global issue as well. So just wanted to share this with you. Just triple check, you can see the presentation, you can see the PowerPoint slide on the screen, yeah? Fingers crossed.
Yes, we can see it.
Great stuff, thank you very much. Okay, so quick agenda then. We'll go through who we are as Sequent, what the problem is we're trying to solve, what do we see as the solution for this, how can we enable this workflow, and then a couple of case studies, with one for our MX Deposit solution, and one for our central solution, and then how that is enabling the workflow as well, and then our summary as well. Okay, so just for oversight then, who is Sequent and what do we do? About 18 months ago, we were bought out by the Bentley group out of the US. So we are now Sequent, the Bentley subsurface company. We manage everything subsurface. Bentley have all the software solutions, that portfolio for the surface solutions. And we're a global leader in the development of visual data science software and collaborative technologies that empowers geoprofessionals, decision makers, and communities to uncover solutions that benefit people and the planet. So we turn complex data into geological understanding to provide timely insights and give decision makers confidence. We harness information to extract the best value, bringing meaning and reducing risk. And we have real world experience across energy, civil, mining, and environmental industries. We believe in constant innovation. So we're really turning profit back into our development and challenging the status quo. So we work in partnership with our clients to ensure we're staying at the forefront of innovation and continually adding value back into our clients' solutions. So what's the issue with the current drill hole to decision workflow, and what are we trying to solve? So this is this scenario that we come across again and again and again. And we have these siloed work streams where the experience, the technical knowledge exists within a project team or within a customer base, but it is siloed within buckets, within these channels. Potentially the teams are split out into their specific technical areas, and work is undertaken and progressed, and data is modeled, but it is done so in isolation of other experiences, of other modeling. And because of that, there is a lack of potential. There is a lack of understanding across the entire project. So here we've got 4 broad buckets of discipline, and people would be exporting and importing different copies of different data sets between each other within the channel, and then potentially even across channels. But there's no understanding of the latest data. Progressively then the work is completed, and you get down towards the bottom of these channels where we have these siloed outputs. And the problem then is when we're trying to combine these data sets from these siloed channels into a consolidated model. And this is where you have duplication and potential overwriting or corruption of data occurring. You certainly have multiple iterations of the same data and the same models and naming conventions. And I have seen some incredible naming conventions over the years, such as version 25, 25.1, 25.1 underscore XYZ underscore MB, and then a date even. And it's just the complexity. It just becomes so tricky for people to navigate that people lose confidence in what they're working on. And so this is the problem. This is what we're trying to resolve. What we want to enable is better connectivity, better collaboration amongst the project team. And so this is our challenge. This is what we were talking about. The experts in their field sitting within their office areas in isolation of each other, and data transferred between, across, over the top of each other, and each person trying to keep track of the individual data sets that they're using for their project. This leads to these points on the right-hand side: the scattered data, the inaccessible data. Network drives are great if they're well managed, but often they're not, and nobody has ownership, nobody has sight of all data. Data becomes lost. This is you spent so much money on collecting this data, whether it's a drill program, a stream sediment sampling program, assay information. A huge amount of investment has gone into obtaining this data, that to lose it is just criminal. Wrong formats, obviously, as well. So very often in my line of work, CSV for drill hole data sets, fine, but then CSV is not as internationally standardly met as it could be, and data often comes through in these different formats, and different people have different versions of those as they import, and data is truncated potentially as is imported as well. Very often the data is too late. I need to progress my project tasks today, but I'm waiting on other colleagues to get to their point of completion before I can access it, before I can progress. And these versions as well, having confidence in who's got the latest data set. We really want to improve that so that everybody can have sight of a sustainable data set and be able to move forward. So that's what we see as a challenge, but there is a driver behind this as well. And what is that? We see it as industry standards. It's no longer acceptable to work in a black box. It's no longer just appropriate that you are skilled in your area so you get your task done. You have to work more collaboratively. The data has to be accessible and available for integration. As soon as you start these larger scale projects, especially, you're working with external consultants, and the projects need to be validated at potentially a regional, national scale, so they have to be industry standard compliant. And yes, the data therefore has to be available for others to take on. And there's brand and reputation as well. Companies want to have good relations with their clients as well as government and regulatory bodies. So they want to be seen as leaders within the technology, leaders within their skill set. There's the digital transformation piece as well. It's a post-COVID world. Companies have had to change the way that they work to allowing for a digitally enabled workforce, and that supports future endeavors as well. The global view of the mining industry and the expertise that exists globally, if you scale that from that's a coverage down to a local project area, having that capacity to include colleagues, consultants, external groups from wherever they are geographically. That post-COVID world has really enabled this linking of people and data. I mean, fantastic to be invited along today to this South African Geological Society conference, and I'm here in the UK, and it's enabled by the Zoom infrastructure, but just an example of that digital transformation that's occurred. And finally, sustainability. Companies are more concerned now with creating a sustainable future. So the efficiencies that have to be met, the understanding that we can't waste resources on traveling for data potentially, or you know, the overheads that would incur, and to the environment. So what can Sequent offer as a solution? And this is where we're driving towards. This is our integrated modeling, our integrated geological model, conceptual models, ground models, whatever we're working towards. In opposition to what we were looking at earlier with those siloed channels of progression and expertise, instead of those channels of work, you can see here all of the arrows are pointing in towards that central model. And the key word that's within this graphic is this single source of truth. There's a lot going on here. There are a lot of arrows, but this is the hub. This is that project, and all parties are pointing towards it, contributing to it, working on the same data. And they're doing it via a number of methods, but it is all from a single pot. Obviously, there's conversations existing between parties. That's great. That's ensuring we've got good communication channels. We're not resolving every data management issue that's ever occurred. What we're doing is providing a framework and providing a collaboration area for these different expert areas to work together and to push forward on. So these groups that were in their previous channels now all interacting, communicating, collaborating, and undertaking their work from this single environment. By doing this, we're avoiding those heavy workflows where you have a lot of automation and repetition. So the geospatial team and the geology team are no longer repeating the amount of work that they could be doing. One team takes it on and the other team sees that result in real time. We can make confident decisions faster. So we're notifying all of the stakeholders in real time. Their alerts to the changes that have been made. They're being emailed, they're being informed via their software solution that the data sets are updated, and they have direct access to the data and the models. So we're increasing the productivity. It allows us to track and understand and peer review these modeling changes more quickly. And by doing that, we're enhancing the efficiencies. So again, we're removing those redundancies, because we're standardizing the processes. So all of the product icons that you can see here, we've got a Leapfrog product icon, our product MX Deposit, this is our Sequent Central solution, and this is Imago. And we'll go through each of those in turn, how they fit this workflow. But the standardization occurs across all of them. So a single project used across multiple platforms is standardized. So codes, pick lists, tables of data, standardized across all of these features, and allows improved efficiencies. We're reducing risk because we're not isolating data. We're improving security and accuracy on the data that we are working on. And so from this, we're learning what's changed, we're learning how it's changed over time, and learning how to fix it, and creating a more coherent audit trail and the workflow transparency as we're doing that. And again, most importantly, we're ensuring this standardization, if we've discussed that. So how do these fit together? Well, so Central is our project and data management collaboration tool. So it's enabling projects and data to be version controlled from within a cloud environment. It is hosted on the Microsoft Azure infrastructure. It allows projects from Leapfrog and Oasis Montage to be hosted in a very easy to navigate environment. It centralizes all of the data in one location, and it allows for the creation of unique and highly collaborative workflows. So as we're looking here on the screen with the video, you've got the users being assigned to projects, files being version controlled within that project, and the entire project history itself being presented in a list format there, and the progression of versions of the project node by node, chronologically tracked. And so I've got real confidence in that audit trail of my project. You can see there's also this visualization component of the solution as well. So we're now moving from the technical team who are modeling the project on their workstations, and we're pushing all of that work up into a cloud environment. And from there, we are further enabling a more wider collaboration because we're passing this model onto a wider project team. It's all managed through a secure user permission-based structure. So you're ensuring confidence and then security onto this project, but you're passing the information onto more project team members, and you're inviting them to give their feedback. That peer review is enabled all through this visualization tool as well. So it creates an iterative cycle of model building, analysis, and peer review, which gives results that, again, increases productivity and efficiency. And it's really easy for these stakeholders, whether they're internal or external, to see at what stage a project is and give their input and feedback so that everybody can make these confident decisions faster, in turn reducing the risk and ensuring the security of the project. We'll touch back on Central in a bit. We've got one of our case studies to look at here. So this second product for this workflow is Imago. And again, an integrated cloud solution. This is going to help us better capture, catalog, connect, and learn from our geological imagery. So a cloud solution, again hosted, this is accessed via a web browser. And what we're looking at is a catalog of, in this case, core imagery, but we can also store chip samples. We can integrate that with CSV data, so we can look at the attribute data that's presented on the screen. We can present both the wet and the dry and derived imagery, so cropped trays and downhole imagery. We can also store any outcrop imagery. Any imagery of any interest for the project can be stored and catalogued, and it is organized by workspace and by project. So again, from within this environment, you're inviting a much wider team to be able to collaborate on and give comment and feedback on the core. Very often, the core that's drilled, for example, is taken to the core shed, it's logged in the core shed. If it's captured in imagery, that's fantastic. But those files can and often do sit idle within a directory on a network drive. By posting and hosting all of this imagery and the metadata associated that to the cloud, you're giving further life to the imagery that you've caught. You can come back to this imagery in years down the line and relog if you need to. You don't have to dig out the trays from the core shed physically or travel to the core shed physically. There's no risk that the core itself is going to decay or the boxes break up and core is lost. At point of capture, all of that information is now available in very, very high resolution, and the metadata associated to it is stored here as well. We can store this imagery, again, it's catalogued in this portal environment, permissive-based access, so it's not just sitting in the core shed. And yet we invite people to connect on it as well. So you can see here, it's editing, its profile is GeoJohn, and we can invite who we need to on this. So at point of logging, that might be our internal team. As we scale our project up and we get down the line, possibly towards resource estimation, this data is going to be of real value when we're looking into the modeling, and being able to display this information alongside our attribute data, our drill hole data, in a Leapfrog or a geological modeling solution environment. Being able to visualize that core presented as a downhole strip, as we have here, alongside lithology or weathering or structural information, gives those geologists really good insight into the accuracy of the logged data, and also the potential to correct any mislogs that might have been made. And then the third product in this workflow, this is MX Deposit. Again, cloud solution. This is our drill hole and sample database solution. So this is in place of ideally CSV files, certainly in place of something like Access, and very, very much competes with the other geodatabases out on the market. It's a completely agile solution. So it is based on a NoSQL database, which means we can very easily make changes to the schema of the database to fit your project data as you progress through your project. It's not limited to a very structured schema that is designed at the point of project outset, and then you're stuck with that down the line. At any point, you can come in here and create new fields on tables, create new entire tables, and change code lists and pick lists as required, but as the administrator. So very permissive management of your database as it should be to ensure accuracy and validation. So there is an entire QA/QC workflow that's enabled here as well. So you can see the receipted information presented here in a chart, and you have that tabular information. And there is a connected workflow all the way through. So we can pull the Imago imagery that we were showing earlier into this environment. So we can display it because the collar, the unique identifier, and the interval information is shared metadata across both platforms. So we can present the downhole lithology against the logged information in MX Deposit here. And the same is true, we can present MX Deposit data back into Imago. So that cross integration that we can enable, again, gives really great insight into your data from whichever platform you're working on and for whichever components of the project team you need to enable. It's all permissive access, it's all email enabled, invitation only. And so you get the best insight into your data as you need it. Totally scalable, so no limit to the number of projects or size you need to plug in. And we can typically deploy this very, very quickly to get customers up and running. There is also a complete offline capability to this solution as well. So if your core shed that you're logging within, or if the field that you're logging, field area you're logging is does not have Wi-Fi connectivity, that's absolutely appropriate that we've got an offline capability. So you check out data sets to your tablet device, you work on those in an offline mode, you have all of the legacy data and code tables and pick lists that are appropriate. And then when you get back to Wi-Fi, get back to the core shed or office, then that data can be validated and synced back into the production database. So a really agile solution available for that. So we're going to have a look at a case study then for both Imago and Deposit. This is using a customer of ours called Free Gold Ventures. They're based in Grand Columbia. Excuse me, that's wrong. The top line is not in Columbia. This is in Fairbanks, Alaska. And yeah, the customer requirement was that they wanted to be able to log their core, but have really high confidence in what they were collecting. The current program has multiple objectives beyond expanding the existing resource and potentially, obviously, hoping to increase its grade, but they also want to advance the project through pre-feasibility. So they wanted to have an accurate, highly validated database which they could progress from. So they wanted to determine the orientation of the higher grade mineralization. They wanted to expand the current known resource and upgrade the resource categories as part of their efforts to advance the project eventually through to pre-feasibility. And yet they wanted to test on, other targets on the project area that may have the potential to host additional resources and host other buried intrusives through the project area. So the solution for them was Imago and MX Deposit. They've been using it for a number of years now, and they've made this video for us that we'll share. You should have audio as well.
Oh, hi. I'm Mark Ramo, working with Free Gold Ventures Limited at the Golden Summit project outside of Fairbanks, Alaska. We're here doing a large coring project. This is our second core shed. The other is exactly like this. We've been using MX Deposit and the Imago software app for about a year now, and it has improved our efficiency drastically. Instead of everyone having a computer with Excel that you have to save and go in and out of a million times, everyone can be logging the hole at the same time as long as you have a different tablet for it. So here you can see I have lithology pulled up, and this is top of the hole to our current position in the hole, which is right here. And if you come over here, you can see Mike's over here logging mineralization for each interval that we've already distinguished. And then as you go through, you can continue, and we even have a oriented log program here. So we have a tablet for the oriented log, structure, alteration, mineralization, RQD, sample. And that is everything we do to log this core. And as I said, everyone on their tablet can be doing a different tab at the same time. So it's highly efficient. And then as soon as you pull out of it, it all auto populates to every computer that's logged into the program at the time. Our internet's very slow right now, so it can take a little while, but that's our only slowdown. And as we're going, we're logging, we're also snapping pictures at the same time. And we found that having consistent lighting is key to being able to capture well-lit photos. So as we go, you can come over here and see the software. This is our buddy Hayes. He's been helping us a bunch. So you just type in the new depth you want to go to, 397.3, move the whole thing over, and then just hit the button and you get your photo right up here. And you can see it's already cropped. It has this amazing auto cropping feature that it'll take each row and crop it individually. So and then once you upload it to the software site, it will lay them all out consecutively. So you get a nice line of your pictures as the core is going down. It's pretty amazing stuff. And yeah, so as you can see, we have our different holes here, and you can go in and it takes a while to load, but this will bring up all the different tabs as I had out before. And that's about how we log core here at Golden Summit. Thanks.
A very helpful Canadian duo helping me out on this presentation there. So yeah, let's say thank you to them. But yeah, you can see how both solutions there really speeding up the logging process for the guys, using it on a touch screen on a tablet, logging the attribute data and also logging the imagery as well, both on the same rack, progressing very quickly through all of their core, all of their drill holes. And that drill hole decision, that speed of capture and the accuracy of capture, the metadata around what they're capturing as well, all being fed into a data set that can be accessed from others. They don't have to get to this remote region of Alaska to be able to visually see the core. They can pull through the data very, very quickly from their remote access points. So whether that's headquarters in the US, experts overseas in Johannesburg, whoever they are, wherever they are, they can connect via these channels, via these software pieces to see that data in real time. So as soon as it's being logged, it's available for the wider team. And again, because of the accuracy, that validation on entry as they're logging it, that increase in confidence, again, just improves that workflow. There's reduced risk. There's less chance that we'll have to go back and relog because you have that confidence in what you've captured and validated at that point of capture. Okay, the second case study is reversed again, sorry. So there's a naming issue. This is around a central solution that we provided for a company called Gran Colombia Gold via an intermediary called GoldSpot. And so Gran Colombia Gold Corp, now Aris Mining Corp, it's a mid-tiered Latin America gold producer focusing on developing and exploring its high-quality project portfolio across mining districts in Colombia and Guyana. The flagship project, this Segovia operation, consists of 4 high-quality, high-grade gold mines in the region and significant brownfield exploration prospects as well. So it was a world-class, multi-million ounce, high-grade gold operation, and it had been producing gold for more than 150 years. So Goldspot and Gran Colombia wanted to work together to leverage machine learning to work within resource exploration. And they set out to help Gran Colombia Gold piece together new geological insights from a literal maze of historic mine data. So their Goldspot's data integration and machine learning solutions allowed them to create robust interpretations for the massive amount of data covering the area's networks of tunnels and ore deposits. But like all geological models, the AI results could only be as accurate as the inputted data. So Goldspot needed a way to bring geoscience experts together to refine this information first. And they had a globally distributed team that needed to collaborate on the same geological model and share a variety of file types to progress this. And so, you know, how could that be done? Well, fortunately, we have our Sequent Central solution, and that's the case study that we've got here. So a way to bring together the geoscience experts to refine that data. And one of the Goldspot colleagues, Sean Central, said, his quote, Sequent Central helped us modernize our approach. We suddenly had a very simple and straightforward way, and it saved us a tremendous amount of time. We knew the version and when it was made. We knew when we had the most current geological interpretation, and we captured notes and caveats from our colleagues. So it provided an audit trail and a version controlling to the project as they progressed chronologically through the project. They were able to give access to their geographically diverse project team, and all of those individuals were able to collaborate and give comment and commit updates to that project in real time. So yeah, their comments were, with Central, we don't have to worry about replicated data or losing track of interpretations because there is a master file which is on the server. It eliminates confusion and the doubt, especially working across the time zones that we have. They felt having an automated audit trail facilitates our workflow internally to a very noticeable degree. It makes us a lot faster. We can respond more quickly, but most importantly, we don't make mistakes. And again, it comes back to this confidence and the accuracy, and the key phrase being the single source of truth. We want people to be working from a single data set, and we want to improve collaboration from that rather than these isolated silos. So this is the data clouds that were modeled in Leapfrog. So the Leapfrog and Oasis Montage projects can be managed within Central. And yeah, all of their project versions, all of their chronology can be tracked. So quite an interesting aspect in this case study, that Goldspot existed and were working with their AI directly for Gran Colombia, but then Goldspot themselves came to us for our Central solution to provide this audit and hosted solution for them. So coming back to Central then, this is why it's such a good solution for this. And again, there's a number of individual products here that we've spoken about so far with Deposit and Imago and Central. And individually, they all work very, very well. But as a total solution, by integrating all of these individuals, you get a total workflow. So Central exists to enable these individuals to access the project, the single project, and the single data sets. And so whereas before we had these arrows pointing node to node across and potentially between each other, we're now again all on this single source of truth. So it's enabling this peer review. So what we've got here represented on the right is these are the nodes of the project as the versions are published from Workstation to the cloud. Each individual publish is given a unique identifier, and its time and dates tracked and name tracked. And you would usually have a comment to explain why you'd published at that point. But it's giving your colleagues the potential to have peer review oversight of each of the individual versions as the project is progressed. So again, it's appropriate for your customer, it's appropriate for your workflows. We're not pushing a standardized workflow, we're enabling multiple workflows via this, this product. It better allows the project team to structure and organize and distribute the workflows. This same track, this same progression here, as on the previous slide, is showing on this line here a very linear progression of the project. So node by node, chronology by chronology, it's being progressed. However, what we also have are these branch lines, and they in turn have their own iteration and progression. So what we're using Central for here is to have this primary track as the master project. And then because of the geography, or because of the complexity of the project, we've actually split out our project team into those modeling zone 1 and those modeling zone 2. So from that master node, from that master point project, each team took a cut of the data, took a cut of the project, progressed it in turn to the point of completion, and then those attributes for zone 2 were folded into the latest revision for the master project. So you can use Central for these multiple workflows, whatever fits your project and your project team the best, you can utilize Central for that. And then the last aspect is the ability to integrate and access and share. So for those of you that use Reflex, the Index Hub, we can API to that data directly and pull that data into the web visualization component of Central so that you can see your planned drill holes, but also your data that is being logged on the rig in real time. And then because we know the orientation and the target end depth of those holes, we can see the projected end of hole as well. So we're using an algorithm to project that. You can see the various data sets coming through from derived grids from Oasis Montage, geochemical data that we can pull in, the resource estimation model, geophysical data, and from multiple sources as well as managing the project progression and version controlling the project. We can do that for any individual data file as well. So whether that's CSV, PDF, anything that is loaded, dragged and dropped, hosted within that central environment, it is all version controlled. So again, that just builds confidence in the data. You have that single source of truth that you're working from. So this is bringing us back to the value of this, this workflow that we've been talking about. By deploying these solutions, whether they are individual as a one-off or all of the solutions integrated together, we're improving the connection from the project team to the data. We're speeding up the processes to capture, connect, and progress the projects from that data sets. We're enabling communication. We're giving channels for teams to collaborate from. And fundamentally, we're improving the confidence that we can have in that data. We know the validation that we're capturing at point of capture, and we can progress from there. And that issue of inefficiencies that at the start of the process that were cascading to become much larger inefficiencies down the line have been zeroed out because we're confident in the data that we're collecting, because we've done validation on entry. Those inefficiencies have been reduced massively. Okay, so just in summary, to say then that using these integrated cloud-based software solutions, we can clean up the data landscape and build a connected workflow that allows for real-time updates, incorporating underutilized data, quickly model iterations, and improve the collaboration with colleagues across these different teams. Data is no longer isolated or lost. It's readily available when needed, and all parts of the process are auditable for quality assurance and quality control to let us make faster decisions with more confidence. This gives us an interconnected data management workflow, enabling teams to work through the drill hole to decision workflow more efficiently and effectively. Gives teams the ability to visualize and share all of this information with the relevant stakeholders.
All right, so yeah, as I said, I think everybody should be appreciating the importance of sampling. I'm just going to emphasize quite a few of the aspects which have been mentioned today already. but touching on quite a few of my personal experiences. As Zeko said, through the last 32 years now, it's getting on for a long time, throughout Africa in a wide variety of commodities and jurisdictions. And as Zeko mentioned, I'm working with Sable now, one of the Datamine software products. And it's really the message I want to try and get across is the need for a flexible solution. And we've heard from a couple of other solutions in the market. So I'm just almost going to focus on more of the background information as to why we need flexibility in our solution. It's just a brief disclaimer there. We'll just go past that. So this first slide really just to emphasize again, actually what Dick Minnitt said this morning about the variety of sampling which we have to gain knowledge of. And one of the big aspects which comes out of sampling is that often it results in some of the biggest and the costliest mistakes. There was a reference earlier to the Bre-X scandal, which culminated in 1997 with billions of dollars wiped off capital markets. And that all stemmed from erroneous practices in sampling. So we cannot overstate its importance. And one of the big issues around sampling is often the cost of acquisition, because a sample may be from field mapping in the middle of the DRC. It could be from a deep WITS drilling program where you're 3,000 meters below surface. So there are great extremes and great costs involved. And very often, and through my experience, not enough value is placed on the geoscientific data held by a business from the samples itself, and obviously the inherent data which comes from the sampling. So it may be analytical data from a laboratory, it could be mineralogical investigations. So the downstream consequences are potentially enormous. So if we just look at a couple of definitions of what we mean by sampling as background, this first one really is just saying it's when we take a portion, and they're saying of ore here, it obviously doesn't necessarily have to be ore, because even in the academic circles, and I believe there are quite a number of students on this talk today, even if you're in academic studies, you might be taking samples for radiometric dating, for example. So this background information is just as applicable to you as even if you're working for a commercial mining operation. And the objective is that it must represent the average composition or makeup of the entire bulk of material. So you can almost put rock in place of ore there. And then the art or the techniques involved in selecting the sample is what we refer to as sampling. The second one, and I'm going to emphasize this a little bit shortly, is that the sampling is a process which is required rather throughout the mining value chain, or the mining life cycle as it's often called. And it can be from both in situ material and broken material, with applications such as resource estimation, grade control, environmental, geometallurgical purposes. So there's a wide variety of reasons why we need to do sampling. It's not just for, checking if it's a concentration of a commodity. Geotechnical is another one. And importantly at the end here, errors in sampling can generate both monetary losses, which obviously we've mentioned with Bre-X are billions sometimes, as well as intangible losses as well. And a third comment here, this is actually taken from the book of Job in the Bible, and this is probably one of the oldest references to sampling that I've ever come across, written probably about 1400 BC. So this actually goes back way before, I know, some of the references Dick Minnitt provided this morning, where it says cutting out channels in rocks. And if you read the whole chapter, you will see some amazing references to aspects of the mining industry, believe it or not. We've heard about the mining value chain or the life cycle already, and this is a fairly common depiction of it. It's depicted in different ways, but it serves to emphasize again that sampling does not stop. Your first samples will often be through greenfields, reconnaissance exploration, through field mapping programs, big geochemical programs, which we'll touch on. Obviously, you want that ultimately to lead to discovery and development of a project, into production when sampling goes into the grade control realm. And even at mine closure, there will be a large amount of sampling going on. That often moves into the environmental aspects, and that sometimes is necessary for many years after the mining operation has actually closed. So because of this long time span, which as you will be familiar, can be 50 years, 100 years, we've heard references today of mines going for. And through that time, you will often have many changes occurring of aspects like personnel, ownership, contractors, even equipment and instrumentation. We saw from the Sequent presentation, all the time there are new integrations with different systems, different products in the market. So all of those issues emphasize the need for standards to be in place, standard work practices. That was also referenced earlier this morning. And a term we'll come to now is often referred to as an SOP, or a standard operating procedure. And no matter how good your IT, your hardware, your software, your people may be, if you don't have methods in place, standards, you're going to encounter issues and problems. So you want standards in place which can be for the whole mining life cycle. And that's really where we're pushing for a flexible solution which can provide that. So don't confuse flexibility with loose data standards. Flexibility means you can adapt to changes in standards, to refinements, and to a variety of standards for different types of sampling. Because as the next slide will illustrate, when we're talking about sampling, there's a wide variety of methodologies. And this also was referred to this morning, is that you don't want to be fixed and tied into a very strict box. So the methods of sampling will vary depending what your application is, what your commodity is, what your geological terrain is, and what your objectives are. So stream sediment sampling is one. We might be sampling water, known as hydrogeochemistry. It could be biogeochemistry, the sampling of plant material. That's seeing quite a lot of research in recent years with successes. Regolith sampling. A lot of people talk about soils. I prefer the term regolith because there's actually quite a few different types of superficial material which get encompassed more under the term regolith, such as lag sampling, maybe some sampling of termite mounds, sampling of gases. And that's before we actually get to sampling of rock, which is probably what many of you will be more familiar with. Very often, unfortunately, when we study and at universities, we don't get exposed very much to these other types of sampling, or any in some cases. So chip or grab sampling, often from field mapping, core sampling. We've seen references to that quite a lot today from diamond drilling. Obviously, chip sampling, again, from reverse circulation or RC drilling. Channel sampling, used a lot underground on stope faces, for example, development ends. It might be done through a mechanical diamond saw, or it might be done manually with hammer and chisel. And there are many other types of sampling as well. So that's really just giving you some background as to the variety we're talking about. And as you may be aware, even somebody like me who's worked for 30 years, I haven't been exposed to all these types of sampling. And there's probably very few geologists out there who've actually had the fortune to use all of them. Some, if they work on a mine, might only work with 2 or 3. So there's a great need also to utilize expertise in the industry. And I'm probably giving a punt here for consultants out there, for geochemists. And this is a bit of a side point, but something I realized this morning. I worked for Anglovaal in my career, which was a big mining company. And 20, 30 years ago, most of those big companies would have in-house experts. They'd have a geochemist, a geophysicist, etc. A lot of that expertise is lost. Either the guys have retired, they've got old, and a lot of the modern mining industry is through junior companies. So I strongly advise you, if you end up working for a small company or a consultancy, utilize expertise out there that have the experience around sampling, because a lot of it, in my experience, has actually been lost. I, for one, don't have a lot of experience in the in-depth stuff, and especially the theory of sampling aspects that was talked about this morning. You need people who have that knowledge, because we don't get a lot of it anymore. So when we obviously are busy with the sampling technique, when we collect the sample, and I'm not going into the theory of sampling anymore or too much detail there, but there will be a number of parameters which need to be recorded. ID, for example, which very often needs to have a uniqueness, is absolutely essential. As you can imagine, when you get duplicates of sample IDs and you get the results back, Now there's a big opening for problems there, because now which sample had those results? And I bet probably everybody who spoke today will have experiences of sample mix-ups and data going on the wrong sample. And then imagine the cost to go and recollect that sample, even if you can actually do that. The location of a sample, absolutely essential. The gentleman, Mark from Sequent, showed quite a lot of examples with spatial representation of the samples and the information. So it might be the depth down the hole, and spatial reference systems referring to map projections. That's a subject of a talk for probably another whole day workshop. But the issues and the conflicts which come around with unknown coordinates or erroneous coordinates is absolutely huge. And again, it doesn't matter how good your system is, there has to be an understanding of that issue. Weight is a big one. We all heard about density this morning. Also, that would be another parameter. The physical type of material. Some of these parameters you might not have experience of, or why do you need that? But very often relationships can come out based on the results. There might be trends and you say, why is all this data so high? And it could have been that the wrong original material was actually sampled with respect to what the application or the objective was. The size fraction, especially when we come with surface geochemical samples. Color, always an issue of debate, but it can be used very to great value. Contamination, when you're doing geochemical surveys, it needs to be taken note of. Is there a metal pipe somewhere? Is there an electrical pylon? I had a case early in my career where somebody didn't take note of that. And the head office consultant came up and said, you've got this anomaly, but what about that high voltage pylon over there? And they hadn't taken note of it. And all of these things need to be recorded in a standard way. That's very important, because a lot of the computer software, the modeling packages now, they give you very powerful functions to do filters and symbolizing on parameters. But if those parameters, these parameters I'm showing, are not captured in a standard way, then those decisions are at risk of being compromised. The topography, who collected the sample, the dates, etc. And obviously there are many other parameters, and we'll mention some others shortly. Now, the next slide, this first phrase, location, location, location. I'm sure every single one of you has heard of that being used in terms of real estate and buying your first house. Rather go for a small property in the right place. Now, when we come to sampling, my phrase that I subscribe to is method, method, method. And that obviously applies to all your geoscience data, is that if you don't have a method, it's the same as having a recipe for making a cake. If you compromise on that recipe, the product will be affected in a negative way. So method, we're referring to a standard operating procedure or an SOP. And when it comes to having your methods in, so I've illustrated the wide variety of sampling, and obviously there is a different method for all of those types. So do not reinvent the wheel. There's a huge amount of experience in the industry, and we have access to these experts all over the world these days. And there will be a method out there. You may need to refine it and tweak it for your particular site, but you don't need to reinvent it from scratch. You need to involve all of the stakeholders. So if you're working on a big mine, like Nicole is, you know, there's no point having one person sampling underground correctly and the next person doesn't care, because then you're going to have disparate data sets, even if it's going into a wonderful database. So you need buy-in from all the stakeholders. And then that has to be implemented. So the SOP has to be implemented for it to actually realize the value and also stay relevant. Mark from Sequent, he raised quite a lot of things where there's integration with Imdex, Imago, lots of other products out there in the market today. And there's things coming up all the time. So you need to stay relevant and make sure your SOPs are continually updated where necessary. And that's also been raised earlier today, is if you don't adhere to this, garbage in, garbage out. That phrase is not going to go away, even with things like AI. I also had a personal experience with the Goldspot company on a Tanzanian gold project a couple of years ago. And it was the same thing. There just wasn't enough quality data for them to get any real results. So I'm a bit cynical on some things, and be aware of these things with AI. They're not going to be the panacea for the next discovery. In fact, there's probably not even been one yet for a new discovery. So when we have our SOPs, there's obviously several scenarios which can occur. The first one is not having any, and then you're not going to have a reliable database. All too often, there's people with 100 spreadsheets on their machine, but not one of them has actually been compiled via an SOP. And that, as many of you also probably will be aware, trying to clean up data in a spreadsheet environment is a recipe for sleepless nights. You may have SOPs in place, but they might not be enforced. So that's, again, maybe they didn't involve the stakeholders, they're not implemented, no database. You may have them and they are enforced, and that's a great start, because then at least you will have a database of some sort of limited use. When I refer to database, it might be paper, as in analog. It could be spreadsheet, it could be SQL, it could be NoSQL, it could be anything. But the point is, it's much better to have enforced SOPs and have a paper database than the previous two. Okay. You might migrate to what I often refer to as a spreadsheet or a light database. So that's when we're dealing stuff with an Excel or Access, for example, where, again, it's progress and it can definitely be used, but again, you may have limitations. Ultimately, what you want to get to, and obviously I work for Sable, so I'm sort of using Sable as an illustration, is that we can provide a data management solution which will give you the maximum value for your geoscientific data by implementing the methodologies which you have, your business practices. Okay, that's really what we're aiming towards. Now, we looked at earlier the mining life cycle, and in a very similar way, a sample has its own life cycle as well. And this is really just an example of a methodology, an SOP in a generic sense for a sample. And obviously, this will be slightly different depending what exploration or prospecting technique you are employing. So it might be stream sediment sampling, it might be channel sampling underground, but the SOP is the first step. And then to implement that, it will have various components. The first of which will obviously be collecting the sample. Now that might be using a hammer and chisel, or it might be taking the sample from a cyclone from an RC rig. Okay, that will be defined in your SOP. Then you will have to capture the sample into a data repository. So in the olden days, that would have been recording it on a piece of paper, could be Excel, could be going into MX Deposit, could be going into Sable. Okay, it's going to be capturing it, and you want the best solution for that, where it's going through validations, for example. The sample will then be submitted to wherever it's being analyzed. It could be a consultant who's doing a mineralogical investigation. It could be the ALS laboratory. They, in turn, will have to have a receipt of the sample. That's quite an important aspect, because that often will not be part of your SOP, because it's an independent institution or establishment, but they should have their own SOP to receive the sample. That's it sounds very simple, but if you're working in, for example, the Congo, you need to go and visit that laboratory, if it's in Lubumbashi, and make sure that you see how the guys received the sample. So be very careful you don't only pay attention to the bits that you've got in your operating procedure. Okay, then they will have to report the results. Again, that might be emailing you a CSV, it might be a direct link to their LIMS system. Then there will be QC analysis. That will be done by yourself. So that will be going back to your SOP again. And again, the solution, or the Sable solution, provides the tools to do that QC analysis. And then you will have a way of accepting or failing the results. So that's passing or failing a batch, for example. And ultimately, you will have analysis and presentation of those results, which may or may not be done in the same solution. It could be going to a third-party application, for example. So that's a sort of very quick overview of a life cycle of an actual sample in a generic sense. So now let's just move on to some more practical examples of samples. So this was in Namibia in 91, where I started my career in 92 rather. A very simple field outcrop, but this was a brief mention here. This is before cell phones, this is before email, before handheld GPS. So in this case, you would go to this location, probably based on an aerial photograph or a topographic sheet. And we can see there's 4 rock types identified here. We've got calcrete on the surface, so that's part of the regolith. We've got a quartz vein here. We've got a gneiss, and we've got a graphitic schist here in the footwall. But now in reality, you as a geologist may be wanting to collect some samples here. So you need a data management solution which will enable you to cater for this scenario. And very often in my experience also, you go into a geologist's office and they've got all these plastic bags over the office floor with pieces of rock in them. There's no labels, they haven't got a clue where they came from, and they sit there for 5 years. You do not want that to happen. So when you capture something in the field physically, it must be managed and stored correctly. Otherwise, it's not going to be of any use. So in this case, we've got the 4 rock types. And the next slide now, I'm just going to illustrate how, when I refer to as a flexible solution, we can now manage this sampling, these samples from field mapping. So this little screenshot is showing you how the Sable data structure works. It's referred to as a tree structure for obvious reasons. It's like you've got branches and different tables coming off from one single one at the top. Each of these blue icons represents a physical table, and each of these tables is made up of one or more fields, which you can see are defined on the right-hand side here. So this is the sampling table for field mapping points, and you'll have an ID, which is where the uniqueness comes in. And then you've got various other parameters. There might be a field weight, what type of sample it was, what was the field batch. And obviously you can have as many fields here as you like. These have field types defined. And where we see lookup, that's referring to a predefined set of terms, which is a very important aspect of how you maintain standardized data. And that's, I'm not going to go into the details of how Sable works. If anybody wants that, they can feel free to contact me afterwards, and we can show you how the actual solution works. But what I want to emphasize is at the mapping table level up here, you would store the site information. So it would be an XYZ location. You might record who the geologist was who visited it, etc. Then when you see one of these blue tables indented, it represents a one-to-many relationship. That's just a database term. So if you've got one mapping site, once you go to the lithology table, MP Lithia, you can store one or more rock types. So in the case of the previous slide, in mapping, we would have one record for this whole site where this geologist is standing. And then when we get to the table below, we will enter 4 records, one for each rock type. And then for each rock type, we can then record a sample information. And it might be more than one sample, because you might want to take 2 or 3 different samples of different orientations for mineralogical investigations. And then you might want to take another sample for an analysis, for example, to find out XRF, what are the oxide constituents of that particular rock. So this next slide here now shows you what the data would look like in reality. So we have logical groupings in these tables at the top. So SMZ was the Southern Marginal Zone in Namibia, which is Pan-African geology. And then the mapping would have been a regional program. You've got an ID for the mapping point. Then you've got several lithologies, and you can see they're separate records here. Those are referred to as branches. And then per rock type, you can then capture one or more samples. So in this case, there was a mineralogical sample taken from the gneiss, and then from the quartz vein, a sample was taken, which for us was analysis from the laboratory. So that's my first example of just the flexibility you need to cater for different sampling scenarios. You don't want to have a fixed structure. I know there's some people, they try and do databases where they'll say, no, you can treat this as a borehole. And yes, you can to a certain extent, but you can also close yourself into a corner by trying to fit everything into one standard. So you need the flexibility, but always within one solution, within one management solution. Okay, this next slide also in Namibia, early in my career, this yellow ellipse represents also an area in the Southern Marginal Zone. For your information, Windhoek is located up here just below the top of the screen. The extent is about 300 kilometers in strike. And the rocks which we had to sample, it was a stream sediment sampling survey. And there was a debate in the beginning as to whether we do it on foot by helicopter. Typically, they said, no, we must do it on foot. So it was about 500,000 hectares. The lithology is where my mouse is running through, coming all the way down. This red area in the south, in the lower left corner, is the edge of the Namib Naukluft Park, hence the very red sand dunes. And we basically had to walk all 500,000 hectares, taking stream sediment samples, approximately 1 or 2 per half to 1 square kilometer. So coming back to the cost of acquisition, as you can imagine, this was an enormous program with great costs involved in accommodation, transport, fuel, obviously the sample and analytical costs themselves. And imagine the cost if you walk somewhere, you say 10 kilometers from the local farmhouse, and the sample bag breaks and you drop it when you get back to Windhoek. Now, the cost involved to go and retake that sample is a little bit frightening. So you don't want your manager coming in and saying, oh, what happened to that huge bag of samples? Okay, so the next slide represents just a little inset of this red area, just to illustrate to you what the terrain was like for some of the area. This mountain here is actually called Kamsberg, similar to the name in the Northern Cape, although it's not. This is the mountain in Namibia. And it gives you a feeling for the terrain which we had to walk over. And you can see, if you go along some of these escarpments, all of the first, second order streams. And imagine you walking here into, obviously before it sort of meets the third order stream, before the confluence, you would take the sample. Then you have to walk up over the ridge, down to the next one, over the ridge, down to the next one. So on average, especially in this area, it was often only about 5 to 6 samples per day. That was the frequency. So it's really just giving you some background as to what people go to collect samples. And this was obviously a greenfields exploration program. Unfortunately, nothing was realized from the program in terms of any mines or developed projects. But, you know, there were very sound conceptual studies done backing up the program. There was nothing wrong with the program at all. And it was extremely important. There were well-designed SOPs behind the program. This was before we actually had an electronic database for this program to store the data in. But if it was done today, within Sable, we would have a similar table structure, but different from the mapping, because stream sediment samples require different parameters to be recorded. So I'm highlighted on the stream sed site table here. So it would again have an ID with coordinates. If it was in a temperate area, you'd be recording colors of the water, for example. But you would record aspects like topography, slopes, environment, any contamination, the aspect of the slopes, and general rock groups, etc., lithology. So you want a flexible solution so that you can have different table structures for different types of sampling. And you can see on the left, and we'll touch some of the other ones shortly as well. Then once you've captured the stream sediment sample site, you would actually go to the samples. And it's part of a one-to-many relationship, because you may want several stream sediment samples with different size fractions. We encountered an issue there where there was a lot of aeolian sand. So we wanted to know whether that aeolian sand was actually going to cause any changes to the analytical results, because you get various iron and manganese absorptions and other issues in very arid climates. So when you're on the sampling table, you've generally got lots of capacity to record QC samples, blanks and standards, CRMs, all that type of stuff that was mentioned this morning, together with more specific parameters, such as the mesh size of the sieves, the percentage of heavy minerals in the sample material, colors, moistures, and so on. Okay, you might be taking radiometric counts of the sample material as well. So there's a whole variety of potential parameters which may be required. Again, per stream sediment site, they often record percentages or the makeup of the heavy mineral concentrate, more specifically in temperate areas where the drainage has actually got water in it than in Namibia, but this just is giving you an example. And then also the makeup of the inorganic component, the clastic component of the sample. And in this one, I'm just illustrating you there the example of a lookup table, which would be controlling the component of the inorganic makeup of the stream sediment site. So were there boulders, were there clays, and then you would record the various percentages. Another sample type here, obviously it's often a very logical progression from stream sediment reconnaissance surveys is to go into soil samples or regolith samples. This was in Barberton, where Seko mentioned I worked early on. For those of you who've had field trips to Barberton, if you're a student, this is the Sheba gold mine in the foreground here. Eureka City is located up on the top of this mountain, and I had the privilege of mapping and sampling this whole, what's known as the Western Cross grid on this hillside down into the bottom of the valley. Golden Quarry, for some of those you know, is located in this steep hillside over here, the richest gold deposit ever found to date in the world, even though it's very small. But it was up to 1 kilogram of gold per ton, for your information, the grade, which, as you can imagine, is quite large. But again, this just serves to illustrate the terrain which often we have to go through to collect samples. Very steep, very inhospitable environment. Actually, even though it's close to the mine, it's still very arduous work to go and collect the samples. So once you've collected them, in this case, these would be regolith samples. There would be a site, and then again, similar but slightly different. So you need that flexibility. So for soil samples, for the regolith type, this is an example of a lookup for regolith type. So this shows you also that in one solution now, you can go and capture and cater for different types of regolith sampling, because it obviously can all be divided up based on logical branches between projects, different geologists, and so on. Then you may have the soil horizon. Okay, very often we'll sample B horizon, but obviously there are other applications where you might sample the different soil horizons, as well as the soil type. These are getting into more sort of detailed parameters, but they are most certainly used in some places. Okay, and then the mesh size, again, also very important. More surface geochemical samples, hydrogeochemistry. So analytes obviously affect composition of water through dissolution. And a couple of examples just mentioned here on the left. Fluorine and associated elements are often analyzed in water samples, as well as uranium and sometimes radon for locating uranium ores. And on the right here in the screenshot, we can see in Sable, we would have different table structures for hydrological sampling, hydrogeochemistry. Also biogeochemistry, as I mentioned at the beginning, the analysis of plant material, where trace elements can be taken up through the ground, through roots into some of the leaves and twigs. And recent studies, especially in Australia, they've seen gold coated on fungi, as well as gold inside eucalyptus trees, which have actually been utilized to locate gold deposits. Quite amazing stuff that people are coming up even now with new techniques. And that's why we need to be flexible and be able to adapt to these things. Now, I'd just like to briefly talk about trenches and pit samples, because this can get quite complicated, and often trenches are not fully utilized. So this is just my little hand-drawn schematic of a trench. And in this case, and actually, if you can think back to the Barberton one, where you've got quite steep hillsides, trenches were used there a lot. If you actually drive around there, you'll see many trenches on the hillsides of the Barberton mountain land. So the trenches obviously can have an orientation. So in this case, it's northeast. Also an inclination if it's on a hillside. So maybe 13 degrees up a hillside. But the geology that you intersect can obviously have a very varying geometry. It could be horizontal or subhorizontal, like one of the chromite or the bushveld seams, or it could also be moderate to steeply dipping, such as these red zones. And based on that, your sampling configuration in terms of its geometry can obviously vary quite a lot. So your database and the structure in your database needs to be able to cater for that. So you just have to try and sort of keep that picture in your mind. I'm just going to go to the next slide. And obviously there's an origin of the trench as well, with the XYZ and a left wall and a right wall. So in the database, what we then need to have is the ability, sorry, I'm just going to quickly go back. Also in a trench, especially if you're dealing with gold, for example, we know there's nuggety effects. So you want as many samples as possible so that you've got a representative estimate of the bulk of the material in the ground. So if you dig a trench and you've got a gold vein going through the trench, it would make absolute sense to take a sample on both sides of the trench to get an idea of continuity, because you can't obviously dig up a massive bulk sample. So if you've dug a trench, it's very similar to doing deflections in boreholes. You would take a sample from both sides and even do it for other commodities as well to get an idea of continuity. So maximize your excavations to the fullest. So inside Sable, we would record the trench and we would record parameters such as if we look at TR1 here, that's one trench, we would have an XYZ of the origin of the trench, its direction and its inclination, length, width, and depth also. That obviously will enable us to portray it in 3 dimensions if we take it into a visualization package such as Studio or Minex or Leapfrog. It doesn't matter what it is, okay? And then once we've captured the trench, we would record profiles. So going back to the previous slide, the profile might be recorded as a horizontal line, as this yellow line is. So you'd say, right, the profile starts at 0 meters and the profile will be 0. In other words, it's going to be horizontal. And then you will take samples from 0, for example, to 3 meters, then from 3 meters to 3.2, and so on and so on. That is very similar to logging core with depth intervals, but you do need a different structure in the database for that. And then you may be recording vertical profiles to go through a horizontal seam. So you might do a profile at 0, at 2, at 4, at 6. And by putting in the appropriate table structure, you can then cater for all those different varieties. And obviously all the time it's backed up by the sampling being dictated by an SOP, and that gets implemented into the database, okay? And then what the data would look like, so you'd have a trench. In this case, we've got a profile at 2 meters. It might be a vertical profile, and then you would have your from and to intervals for the relevant samples. Okay, and it could be a chip sample off the face of the trench, for example. Okay. Now, if we move on from that, we come to core samples, and this is going back in history a little bit. This screenshot is of an SOP, actually, you can see by the name. And this was from Angloval in 1991, when I was involved in the very deep Witwatersrand drilling program for the Sun and Target projects. It was actually the biggest deflectional drilling program in the world has ever had outside of the oil and gas industry. We had in excess of 50 drill rigs in the field at one time, all drilling more than 3,000 meter boreholes, which is quite difficult to imagine today. There's not really anything going on like that now. But as part of this SOP, which you can see was written on an old-fashioned typewriter, they're emphasizing the high cost of exploration. You can insert sampling there. Is extremely important to ensure that the results are as reliable as possible and that the company gets the maximum benefit from its expenditure. And those comments have already been mentioned throughout today. And then they're emphasizing here the great care must be taken of the reef intersections, insert and sampling, to give true and unbiased values. And then also very important, in order to obtain the above, strict security precautions must be maintained. There's been references through today of some of the mineral legislation codes from the stock exchanges, and security and auditability is an extremely important aspect of compliance. So I was very privileged to work for Angloval because we had some very wise people who were very aware of the importance of these aspects way before they were implemented for the stock exchanges, which provided me very sound training. And this was obviously before I done my studies, but in industry, these things have been known about for a long time and implemented, but they're not always implemented even today, okay? And this SOP is actually about 18 pages long, and it goes through everything from the drilling, through the sampling, through the crushing, pulverizing, etc., which we as geologists actually had to do ourselves. So we did all the sample prep before the sample went to the laboratory. So just to illustrate what was going on back then, this schematic is just a section. So the reddish line is the surface. Then we would drill the mother hole, this D0, down and intersect a gold reef. In some of the holes, there were more than 50. And the protocol stated there had to be a minimum of 4 deflections drilled on per reef. So you can imagine when there were 50 reefs in one hole, how many deflections there were. And then every single one of those deflections had to be sampled, as well as being logged at a scale of 1 to 10. Literally hand drawing pebbles and clasts, defining the different types of pyrite, etc., etc. So the importance on the sampling was unbelievable, actually. And the amount of effort and close scrutiny that was put on it, that it was done properly. So in terms of the Sable database structure and how it was managed was, you would have a table for the diamond hole, the collar of the mother hole, the D0. Then this DD collar table is where we cater for all the information for the deflections, D1 and so on. The fields being shown in the right-hand side here. So you would have parent deflection, which obviously when it's D1 would be D0. Then you would have a top of deflection, depth, etc., for all these individual blue lines. Then you'll eventually get down to the samples. So per deflection, once you've gone through the reef, you would then be capturing the sample information. And again, slightly different from some of the other sampling tables of the other methods, emphasizing again the flexibility of your solution. This is an extract of some of the outputs from the sampling. As you can see, before digital things were in place largely, we logged it at a scale of 1 to 10, very detailed descriptions. Obviously, this is, and what I wanted to touch on was that this program was largely the motivation for the development of the Sable solution. So it was way back in 1983 when the originator, Marsha, who will be talking tomorrow, developed this solution from scratch. So it emphasizes that it was developed on the most sound principles and probably one of the most challenging exploration projects which the world has ever known. And that's where the origin of Sable comes from. And you can see in this particular image here, we've got the samples defined. Normally they were about 20-meter samples. And as I said, as part of the SOP, every deflection had to be captured. It was called capture process by an independent geologist from the one who actually managed the drill rig for security reasons to prevent fraud. So this was way before Bre-X. And then the individual geologist, so if it was myself, I would capture the core through conventional drilling from the Free State, from the farm. It would be in a padlocked wooden box. You drive it back under your own personal supervision to Klerksdorp. You crush it, or you log it first, you crush it, you pulverize it, you bag it, get sent to the laboratory. We never got to know the gold results for those samples. The security was that strict. Now, obviously, if they'd had an SOP like that for Bre-X, Bre-X wouldn't have happened, but that wasn't the case. But it can be done properly. Just moving on to core samples in coal environments, slightly different. So in base precious metals, the sampling can often have independent variables, depths rather, from the lithological logging. In the coal industry, and this has come from actually a big consultancy who does a lot of coal work, generally the coal sampling will always be coincident with the coal lithological boundaries. So the table structure in the database is slightly different. So we have the sample table for the coal being below the lithological table. It's just a slightly different relationship in the database. And then obviously we've got subsequent tables to record the laboratory, the method, and then the various parameters used in the coal analysis sector. And you've got different weights and check weights and various things. So it just looks a little bit different. And there's just a quick shot of also a coal project I managed a few years ago in the Ermelo coal field. So you would see in this case, the sample would be taken from the top to the bottom of the coal seam here. Okay, and that just agrees with that table structure shown in Sable there. Okay, how am I for time, Nicole? Am I? Or Zeko rather.
Yeah, you're still good, Ellen. Just, yeah, you can continue.
Okay, thanks. I will try and speed up a little bit.
Okay, thank you.
Okay, just carrying on. It's really just illustrating more examples. Obviously, sampling is essential for grade control. So when you're in a producing mine environment, and sorry, the definition there is really to ensure that the material being fed to the mill is of economic grade and that any fluctuations are minimized. So through your grade control sampling, you basically just ensure a consistent feed, because obviously that has lots of downstream consequences because processing plants, etc., would have been planned on estimates from previous sampling to the grade control programs. We obviously see it happening both in open pit and underground. So in open pit, it may be from the blast hole cuttings or chips, which is used to classify bench reserves into various grades or waste. And it can also involve taking ad hoc sampling from equipment, from trucks or shovels, etc. And then in the underground environment, similar, but again, different scenarios. So I'm just emphasizing yet again, the flexibility of your solution is that one sort of configuration of sampling and related tables will not necessarily fit everything. Whereas in underground, it may be from stope faces, also from carloads or draw point muck piles underground, or diamond drills. If we just look at open pits, that's just emphasizing again, and the picture really just shows us, in this case, it might be a blast hole where you only take one sample, and that may require its own table structure in your database management solution. Or some open pits use RC drilling, in which case you may be doing samples at 1 meters or 3 meter composites. So you need to be able to cater for those different types of configuration for your samples. In this little screenshot here, we've got a slightly separate part of the database structure where we've got also some different header levels. So we've got bench level, we've got block section, and that enables us to logically group the data.
Sorry, Ellen,
as you can
about 5
imagine.
minutes, less than
Okay,
5
thank you.
minutes, yeah.
As you can imagine, if you're taking grade control samples for a 50-year mine, the number of records will be tens of thousands. So you need very sensible logical groupings to ensure the performance of your database. And this table is called GeoSamp because this would be an example where the lithological logging is the same as the sample intervals, for example. So it's a slightly different configuration. Okay, RC there's just another example from and tos, and that might be 1 meters or 3 meters. And you would always need the ability to store the QC sample type and various other QC required parameters. Okay. Underground, as I've mentioned, could be from stope faces or even from the roof. In underground environments, it often can get quite complicated in terms of locating the sample. Very often it's related to underground survey pegs. And you'll see in this case, again, a slightly different table structure. So we would have a mapping observation and we would have samples. But in the mapping observation table, we would need to record the relevant information to correctly locate and obviously then visualize that sample site. So we need things like survey pegs, distances from the pegs, and inclinations of the sample profiles, for example. Okay. So coming to the end, just a couple of concluding comments with regards to sampling is that, first of all, it's always essential throughout the mining value chain or the mining life cycle. We absolutely need methodologies and SOPs for our sampling. Otherwise, it's going to be a mess. There are a great many varieties of sampling in how they are collected. And obviously, there are many intricacies in that, which have been covered in other talks and will be more tomorrow. We always require one central solution. That's reaffirming again a message which came out earlier. Otherwise, again, with so many people involved in changes throughout that mining value chain, you can imagine you do not want different methodologies of sampling because you're just not going to be able to trust the data and the decisions thereof. Flexibility is key. Okay, flexibility, but being able to maintain standards and the methodology. And Sable is a solution which most definitely can provide that for you. So with that, I'd like to thank you very much for your time, and I hope your eyes haven't closed too much. And if there's any questions or comments, I'd gladly take them.
Thank you, Ellen. Great presentation. Any questions for Ellen?
Sergio, if there's no questions, I'd like to ask one. Ellen?
Yep.
I'd like to take you sort of back to the beginning of your presentation where you spoke about, with, merging companies, etc., those types of things, and, looking at sort of different standards. And the tricky part is, post obviously capturing that data and then using it for, whatever purpose, becomes a bit tricky because, if you've got different logging standards or different lithological naming conventions, piecing stuff together across boundaries, etc., becomes a bit tricky. So, how would one ideally handle that? Would you change, data to become one standard, or would you rather post your database once you've extracted the data, then look at, changing and aligning your data sets so that you can use them as one?
Yeah, it's a very good question. So, we obviously, being in the business we encounter that many times because we get a company, they say, yes, we'd like to implement Sable. And we say, okay, have you got historical data? They say, yes. And sometimes it may be 3 or 4 different versions of data. So to address that question, the first thing is to go back to the data set and say, okay, have you got the SOPs which were used for that generation of data? If they have, that's great, then there's a tick. If they haven't, then basically the client needs to make a decision to say, okay, if we don't, can we trust it? If they can't trust it for whatever the objective is, so say it's a resource declaration, then basically we can still take it into the Sable solution, but we will leave it almost as invalid data. So they can use it for reference purposes, because you certainly don't want to leave it, and you don't want to leave it outside of the solution, because every piece of geoscientific data will have value of some sort or another. So within Sable, because we use these logical groupings in a tree structure, we can keep data sets separate if they do not comply to the same standard. If data obviously does have the relevant SOPs, and it can, it'll pass an audit, for example, from a CP, from an external check, then we will bring that into the current operating standard for that business unit, for that company. Now, sometimes that requires some translations in the data, but generally that's not a big deal. So if we've got 2 different standards, 2 different SOPs, we would sit with them with the client and say, okay, this person used the code P for a primary sample, you're using the word primary. Then we do a mapping process. So we basically amalgamate the data into one standard, but we will only do that if it can be trusted. And that comment has come up through the day. It's like, well, if it can't be trusted, it's not of any use. Even if it can't be trusted, I definitely wouldn't get rid of it, if you know what I mean. So it really depends on how much documentation you've got to back up the data set.
Yeah, I mean, these are things that were rigorously, sampled and captured with, the SOPs in place. So that's not the challenge, but the challenge now is, using data from, another property, because you're sitting on a boundary and you're trying to translate stuff across.
Yes.
And this guy's logged it differently, or, logged and captured it differently to the other side. So it's just marrying those 2, I think, becomes the challenge. And I personally don't feel that changing the primary data should be where it should happen. I think it should happen outside of the database, post, extracting it and then making sort of changes or writing macros or whatever it is to change the data so that it aligns.
Yes. Yeah. No, I mean, that challenge is never going to go away, I don't think, because you're not going to, even today with the globalization, and you get sort of countries that try and implement, okay, this is the coal standard for Australia, whatever, but South Africa doesn't want to do it that way. So you're always going to have that battle. And it's not necessary to always say one standard or methodology is better than the other one either. So it's I hear what you're saying, and there's no quick solution to that issue. But what you do want is a standard moving forward. In other words, you don't want to be in a state where you're continually using a mixture of standards. So whatever your solution is, it needs to be implementing a standard.
Yeah, I think, and that's as you say, that's what has to happen going forward, is now looking at joining, those things into one, essentially.
Yes.
Yeah. Okay. No, thank you.
Thanks, Nicole. Great question. Any other questions, comments, thoughts? Marcia? Oh, is that a clap?
Sorry. It was meant to be. I always get confused with this for some reason. Nicole, I just thought, you can go and speak to Louise at Impala. Over the years, they had many joint venture partners on their boundaries, and I think they would exchange data, the way geologists do. And I know that Louise would sit there, and I don't think it was only her, probably Pencil here as well. They would sit, study this other thing, and they would change it into their own standard. And I think they also often thought they had more data on this side of the fence, and they probably knew better. But I'm not saying that they're arrogant, but they may have had such a thing. because they've been very strict and disciplined over the years in Impala in their protocols. But from an IT and database perspective, you really shouldn't change databases. So, I mean, that's now the software engineering thing. You should rather extract the data, as you said. Make common reporting and extraction. And if some global people want to look at the data from different databases or slightly different standards, you should rather handle that in the reporting of it, you know, and have different reportings. I don't know, I mean, that's another viewpoint, but of course they're not geologists, you know, no, software engineers aren't geologists, so it's not easy, eh? Yeah.
Yeah, as you know, as Ellen says, it's not saying that one is more right than the other. It's just finding a solution currently that suits everybody.
Yeah.
Obviously, the one thing also is, like Marsha says, you don't really want to change either of the data sets. So obviously, if the new sort of client or whatever has got the money, it's rather to do a program of auditing. So in other words, do a new set of work to confirm that that other data set is acceptable. Like we do with sampling and assay results, you know, you do a 10% audit check or something like that. So it's almost doing twinning of holes and twinning of sampling programs or whatever, but not the whole thing. Then you don't have to change the one data set, and you've got a new data set which is according to your standard, but it's also confirmatory of what was done before.
Okay, yeah, it's a good suggestion as well.
Yeah.
Okay.
That's very good advice, Alan. Yeah, because you don't want to get rid of anything, because money was spent to get that information, even if it doesn't comply with what.
No, it's like if you say, for example, if you take an old trench and you find a trench, you might have results from that trench. That's an easy example, because then you can just go in and resample the trench. You know what I mean? It's obviously more problematic when it's grade control data or it's a big drilling program, but it's the same principle.
Definitely.